Tonight, our journey takes us to a place that exists right now on our own planet, a place that is not distant in space or hidden in fiction, but quietly present beneath the surface of the world we think we know. It is a place more alien than the surface of the moon, not because it is far away, but because it remains almost entirely untouched by human experience. We're going down, slowly, patiently, toward the deepest part of the Earth's oceans, to a realm shaped not by light or air, but by pressure, darkness, and time. Before we begin, if you find comfort in these long, unhurried explorations, subscribing helps others find their way here too, one quiet listener at a time. But for now, let yourself settle in. There's nowhere you need to be, no pace you need to keep. Just allow your attention to drift as we begin this slow descent. We tend to think of Earth as a finished map, a globe filled in with detail, borders clearly drawn, every mountain measured, every surface photographed. From above, the planet appears complete, almost familiar, as though there are no mysteries left large enough to surprise us. Satellites pass overhead constantly, tracing coastlines, charting forests, mapping deserts down to the smallest detail. We can zoom in on streets, on rooftops, on individual trees. It gives the impression that nothing remains unseen, but that confidence dissolves the moment the land slips beneath the ocean. At the water's edge, certainty fades. The maps become softer, less precise. What we call images of the seafloor are not photographs at all, but interpretations, assembled from echoes and assumptions, painted in broad strokes where detail is impossible. The deeper the ocean becomes, the less we truly see. And at the very bottom of it all lies the largest blank space on the map, a place so deep that even our best technology struggles to describe it clearly. The Mariana Trench is not a hole in the earth in the way we might imagine. It is a vast, elongated scar in the planet's crust stretching for thousands of kilometers across the western Pacific, deeper than the tallest mountains are high. At its lowest point, known as Challenger Deep, the ocean plunges nearly 11 kilometers downward. If Mount Everest were placed there, its summit would still be hidden beneath more than a mile of water. But depth alone does not explain why this place feels so distant. As you descend through the ocean, something subtle begins to change. Light fades quickly, thinning into deep blues before disappearing entirely. The temperature drops. The water grows heavier. Pressure builds quietly and relentlessly, adding another layer of force with every few meters. At the surface, the weight of the air around us is something we rarely notice. Beneath the sea, that weight multiplies, stacking itself again and again, until the pressure becomes so immense that it can bend solid steel and reshape materials at the molecular level. By the time you reach the bottom of the trench, the force pressing in from all sides is more than 1,000 times greater than what we experience in everyday life. This is why, in a strange and counterintuitive way, space was easier to reach. Space is empty. It can be sealed against. The trench is not empty at all. It is full, saturated with pressure, a constant presence that pushes back against anything that enters. It is not a void. It is an environment that actively resists us. And yet, we have always been drawn to it. When we imagine such depths, such darkness, we often imagine silence as well. A perfect stillness, untouched by motion or sound. But that assumption, like so many others about the deep ocean, turns out to be wrong. Down there, the Earth is not quiet. Sound travels differently under immense pressure, bending and stretching across vast distances. Low-frequency vibrations can move through the deep ocean for thousands of kilometers, carrying the echoes of storms, earthquakes, and distant ships far beyond their point of origin. The trench becomes a kind of echo chamber, a place where the movements of the planet itself are recorded and remembered. And among those sounds are others, more puzzling ones, signals that do not easily match any known source, calls that seem structured, almost deliberate, yet remain unidentified. They are rare, subtle, and easy to dismiss, but they linger in the recordings, quietly resisting simple explanations. When we encounter something like that, something we can hear but cannot see, something that comes from a place we barely understand, our imagination tends to fill in the gaps. We picture something vast, something hidden, something waiting in the dark. But the trench holds stranger truths than monsters or legends. One of the most unsettling discoveries ever made, there was not a new species or an ancient survivor. It was something ordinary, something unmistakably human, resting on the sea floor in a place we were never meant to reach. It does not belong there, and yet it arrived before we did. We'll return to that story later. For now, let the surface world fade. Let the noise of everyday life soften and recede. Imagine the slow, steady descent through layers of water that grow darker and heavier with each passing moment. This is not a journey defined by danger or spectacle. It is a journey into scale, into patience, into a part of our planet that operates on rules entirely its own. And as we continue downward, leaving light and certainty behind, we begin to understand just how little of this world we've truly seen. We like to imagine that the age of blank spaces has ended, that the world has been carefully filled in and smoothed over by satellites and sensors, that nothing truly large remains unseen. When we look at a globe today, it appears complete, wrapped in lines of latitude and longitude, coloured with terrain shading, annotated with names that suggest familiarity and control. It gives the comforting impression that the Earth is no longer a mystery, only a collection of facts waiting to be memorized. This feeling is reinforced every time we pinch and zoom across a digital map, gliding effortlessly from the curve of the planet down to the detail of a single building. It feels like vision, it feels like knowledge, but it is in many ways an illusion. That illusion holds together only as long as we stay on land. The moment the continents slip beneath the sea, the certainty we rely on begins to thin and the map quietly starts to lie. The oceans dominate this planet not just in area but in volume, yet they remain the least understood part of Earth's surface. While nearly every mountain peak has been measured directly and photographed repeatedly, much of the ocean floor has never been seen at all. What we often think of as maps of the seafloor are not images in the ordinary sense. They are translations, indirect impressions assembled from sound. Ships cross the oceans emitting pulses of sonar, listening for echoes that return from the depths below. From the time it takes for those echoes to come back, scientists estimate distance. From the strength and pattern of the return, they infer shape. But these measurements are sparse, stitched together from narrow paths where ships have travelled, leaving vast areas between them filled in by educated guesswork. Imagine trying to understand a city by listening to a handful of echoes bouncing off its buildings while blindfolded, then sketching the streets from memory. That is closer to how much of the ocean floor is mapped than most people realise. In many places, the resolution of these maps is so coarse that entire mountains could be hiding between the data points without being detected. The deeper the water becomes, the less precise these interpretations grow. At extreme depths, the seafloor turns into a blurred suggestion, smoothed into gentle slopes and valleys that may not truly exist. The Mariana Trench represents the most extreme example of this uncertainty. It is the deepest feature on Earth, and paradoxically one of the least clearly seen. Despite its importance, despite decades of study, its contours remain elusive. There are sections of the trench where the exact depth is still debated by tens of meters, not because scientists lack skill, but because the environment itself resists clarity. The trench is not hidden by remoteness alone. It lies beneath some of the busiest shipping lanes in the world. It is hidden by force. The water above it is not passive. It absorbs sound. It bends signals. It distorts measurements. Even light, our most trusted tool for understanding, is erased completely long before the bottom is reached. Cameras become useless without artificial illumination, and even then, what they reveal is only a narrow cone of visibility surrounded by endless black. When we say the trench is unmapped, we do not mean it is unknown in the casual sense. We know where it is. We know roughly how deep it goes. We know how it formed. But knowing that something exists is not the same as seeing it, and the difference matters. On land, our maps are confirmations of what our eyes already understand. In the deep ocean, maps often replace vision entirely. They become the story we tell ourselves about a place we cannot witness directly. Over time, those stories solidify into certainty, even when the evidence remains incomplete. The trench exposes how fragile that certainty really is. It reminds us that much of what we believe we know about the planet rests on indirect measurements and assumptions layered carefully on top of one another. There is a quiet humility in this realization, one that contrasts sharply with the confidence of surface maps. The Earth beneath the oceans is not arranged for our convenience. It does not scale down neatly or reveal itself willingly. Its deepest features exist in conditions so extreme that even our best instruments must struggle just to survive long enough to take a measurement. This is why, even today, the largest blank space on the map is not some distant desert or polar ice cap, but a vast, crushing abyss hidden beneath ordinary blue water. The Mariana Trench is not a void waiting to be filled in by better graphics or sharper sensors. It is a place where the very act of measurement becomes difficult, where pressure deforms equipment, where signals weaken and scatter, where certainty frays at the edges. It is not distance that keeps this place obscure. It is the sheer physical force of the environment itself. The deeper we attempt to see, the more resistance we encounter, as though the planet is quietly reminding us that not every part of it is meant to be easily known. This realization changes how the descent feels. We're no longer traveling toward a point on a map. We're moving into a region where the map itself begins to lose meaning, where numbers and outlines give way to conditions and constraints. The trench is not simply the deepest location on Earth. It is the clearest example of how limited our vision still is, and how much of the world remains defined not by what we see, but by what we cannot. As the idea of maps begins to dissolve, as outlines soften and certainty fades, another realization quietly takes its place, one that explains why the deepest parts of the ocean resist being known at all. It is not secrecy in the human sense, and it is not distance measured in kilometers. It is weight. An invisible, patient force that increases steadily, meter by meter, until it becomes the defining condition of the entire environment. Pressure is easy to ignore at the surface because it is evenly distributed, balanced, and familiar. The air presses down on us constantly, but our bodies evolved within it, and so we rarely notice its presence. It feels neutral, almost non-existent. The ocean changes that perception very quickly. With each step downward into the water, pressure accumulates with a simple, unforgiving logic. Roughly every 10 meters, the weight of another entire atmosphere is added, the same amount of force exerted by all the air above us at sea level. At first, this increase feels abstract, a number rather than a sensation, but the stacking never stops. At 100 meters, the pressure is already 10 times what it is on land. At 1,000 meters, 100 times. By the time the seafloor of the Mariana Trench comes into reach, more than 11 kilometers below the surface, the pressure has grown to over 1,000 atmospheres. It is difficult to imagine what that means because there is no direct analogy in everyday life. It is not the sharp impact of a blow or the strain of lifting something heavy. It is uniform, constant, and absolute. It presses from all directions at once. Steel hulls that feel rigid and invulnerable at the surface begin to flex like thin sheets. Glass shatters not from impact, but from being asked to hold its shape against a force it was never meant to resist. Bones, which feel solid and permanent to us, would not snap dramatically at that depth. They would simply fail, compressed beyond their ability to maintain structure. This is why the trench is not merely deep, but fundamentally hostile to the kind of life and technology that thrive on the surface. Pressure does not behave like an obstacle that can be pushed aside. It changes the rules entirely. Materials behave differently. Chemical reactions shift. Biological processes slow, warp, or stop altogether. Even the most basic assumptions about how matter should act begin to break down. This is why early explorers of the deep quickly learned that brute strength was useless. Thicker walls alone were not enough. The environment demanded a different approach, one that accepted the force rather than tried to overpower it. The comparison to space helps clarify this difference. Space is often described as the ultimate hostile environment, and in many ways it is. It is cold, airless, and flooded with radiation. But it is also empty. Engineers can create pressure where none exists, building a sealed interior that mimics the conditions humans need to survive. In space, the danger comes from a lack of pressure. In the trench, the danger comes from an excess of it. There is no easy way to carve out a safe pocket when the surrounding force is actively trying to collapse everything inward. This inversion makes the deep ocean uniquely challenging. A spacecraft fights to keep pressure in. A deep-sea vessel fights to keep pressure out. And the deeper it goes, the harder that battle becomes. Over time, scientists came to understand that pressure is not just a mechanical threat, it is a biological one. At extreme depths, pressure begins to interfere with the fundamental machinery of life. Proteins, which must fold into precise shapes to function, can be distorted. Cell membranes, which rely on a delicate balance of fluidity, can stiffen or leak. Enzymes slow down, nerves misfire, metabolism falters. For organisms adapted to surface conditions, the descent into the deep is not a dramatic crushing death, but a quiet systems failure, one process after another slipping out of alignment. This realization reframed how scientists thought about life in the trench. Survival there was not a matter of armor or size, but of chemistry. To exist under such force, life had to be built differently from the inside out. The pressure was not simply something to endure, it was something to incorporate, to make normal, to rely on. This is what makes the trench feel so alien. It is not just darker or colder than the surface, it operates on a different set of constraints. The force pressing down is so great, so constant, that it shapes everything within it, from the largest geological structures to the smallest living cells. The water itself becomes heavier, denser, more demanding. Even movement changes. Every motion requires more energy. Nothing happens quickly. Everything slows. And yet, for all this weight and stillness, the trench is not inert. It is not frozen in silence. As we sink deeper into this pressurized world, as the idea of crushing force settles into the imagination, another assumption quietly falls apart. We tend to picture such depths as soundless, sealed off from the restless surface above. But pressure, it turns out, does not smother sound. In some ways, it preserves it. The same force that makes the trench so difficult to reach also allows vibrations to travel in unexpected ways, carrying whispers of the planet's activity into the deepest darkness. As the weight of the ocean becomes the defining presence, as pressure settles in as something more than a number, it feels natural to imagine that everything else must fall away. Darkness suggests emptiness. Emptiness suggests silence. It is an assumption so intuitive that we rarely question it. When light disappears and movement slows, we expect quiet to follow, a perfect stillness untouched by vibration or disturbance. For a long time, scientists shared this assumption as well. The deepest parts of the ocean were imagined as acoustically dead zones, places where sound could not survive, where nothing moved fast enough or violently enough to make itself heard. The trench, in this picture, was a mute void at the bottom of the world. That idea began to unravel the moment we started listening instead of looking. When researchers first lowered sensitive listening devices into the deep ocean, they did not expect much. These instruments, called hydrophones, are essentially underwater microphones designed to detect vibrations across a wide range of frequencies. Encased in thick protective housings, they are lowered kilometre after kilometre into the darkness, passing far below the reach of sunlight and into a realm where human senses are useless. The expectation was simple, a baseline of quiet, perhaps punctuated by the occasional distant rumble. What they recorded instead was anything but silent. The deep ocean revealed itself as an environment saturated with sound, layered, complex, and constantly active. The reason lies in the physics of water under pressure. As depth increases, temperature and density change in subtle ways, creating layers that bend and guide sound rather than scattering it. In certain depth ranges, these conditions form what oceanographers call a deep sound channel, a natural acoustic corridor where sound waves become trapped, unable to escape upward or downward. Within this channel, low-frequency sounds can travel extraordinary distances with very little loss of energy. A noise made on one side of an ocean basin can be detected thousands of kilometers away, preserved and carried along by the water itself. The trench sits beneath and alongside these channels, acting not as a barrier to sound, but as a receiver. It gathers vibrations from across the planet, collecting them in the deepest places where pressure is greatest. When hydrophones listen from these depths, they hear the Earth in motion. They record the slow groan of tectonic plates grinding past one another far below the seafloor, a low, continuous sound that reflects the restless nature of the planet's crust. They capture the distant thunder of underwater earthquakes, some occurring so far away that their surface effects go unnoticed by people above. Even storms leave their mark. The energy of a powerful typhoon can penetrate the water column, its presence detectable in the deep long after the clouds have dispersed and the winds have faded. The surface world, it turns out, does not stop at the surface. Its movements echo downward, carried patiently into the abyss. Alongside these geological and meteorological signatures are the sounds of life. Whales, particularly the larger species, communicate using low-frequency calls that are perfectly suited to travel through water. A single call can cross entire ocean basins, slipping into the deep sound channels and moving outward like ripples in time. From the depths of the trench, these calls arrive as distant, mournful notes stripped of direction, detached from any visible source. The trench hears wails that may be hundreds or even thousands of kilometers away, their presence reduced to sound alone. In this sense, the deep ocean becomes a listener, an archive of biological communications spread across unimaginable distances. For scientists, many of these sounds are familiar, catalogued, and understood. They can be matched to known processes and species with reasonable confidence, but not all of them fit so neatly. As recordings accumulated over years, certain signals began to stand out. Short, structured sounds that did not match known whale calls, metallic-sounding vibrations that did not resemble geological activity, patterns that repeated without obvious cause. These anomalies were rare and subtle, easy to overlook, but persistent enough to resist dismissal. When sound is divorced from sight, interpretation becomes difficult. A vibration carries no image with it, no sense of scale or intention. A small source nearby and a massive source far away can produce similar signals by the time they reach a hydrophone. This ambiguity leaves space for uncertainty, and uncertainty invites imagination. Researchers approach these sounds cautiously, aware of how easily speculation can outrun evidence. Many unexplained recordings eventually find mundane explanations, trace back to ice cracking, equipment artifacts, or unfamiliar variations of known biological calls, but some remain unresolved, not because they are extraordinary, but because the environment makes certainty elusive. The trench complicates even listening. Pressure affects equipment, currents shift positions, sound bends unpredictably. The same force that preserves vibrations over long distances also distorts them, reshaping their signatures as they travel. What arrives at a hydrophone is often a ghost of the original event, altered by the journey. This creates a strange inversion of our expectations. In the darkest, most remote place on Earth, the planet is not silent at all. It is attentive. It listens to itself constantly, recording its own movements and the lives that move through it. The trench is less a void than an echo chamber, a place where the world's deepest sounds converge and linger. This realization adds another layer to the descent. The pressure that defines the trench does not smother activity, it preserves it. The darkness does not erase information, it carries it in different forms. And as the recordings show, while many of the sounds that reach these depths can be identified and explained, others remain just beyond our ability to classify. Reminders that listening, like mapping, is an imperfect way of knowing. Some sounds make sense once you know what to listen for. Others resist that comfort, existing quietly at the edge of understanding, waiting to be noticed again. Once listening became routine, once the deep ocean revealed itself as an active acoustic environment rather than a silent void, patterns began to emerge. Many of the sounds captured by hydrophones fit comfortably into categories we already understood. The low rolling growl of tectonic plates shifting against one another became familiar, a constant reminder that the planet is never truly at rest. Sharp, sudden pulses could be traced back to underwater earthquakes, their energy radiating outward through the rock and water alike. Even human activity left an unmistakable signature. The steady rhythmic thrum of large ships passing far above the trench travelled downward and lingered as a distant mechanical hum, a reminder that the surface world constantly intrudes, even in places we imagine as isolated. Whales too became regular visitors in these recordings. Their calls, slow and deliberate, slipped easily into the deep sound channels and arrived at the trench stripped of direction, like voices carried through fog. Over time, researchers learned to recognize these sounds the way one learns a language, identifying the speaker without ever seeing them. But alongside this growing familiarity, there remained a smaller collection of recordings that refused to settle into known explanations. They were not loud, they were not dramatic. In many cases, they were barely noticeable at all, brief anomalies buried within hours of otherwise predictable noise. A strange metallic twang that appeared suddenly and vanished just as quickly. A sequence of tones that rose and fell in a pattern that did not match any catalogued whale call. A low vibration that seemed too structured to be random, yet too irregular to be confidently assigned to geology. These sounds did not announce themselves as mysteries. They lingered quietly, resurfacing only when someone listened closely enough to notice that they did not quite belong. Scientists approached them with caution, aware of how easily unfamiliar data can be misinterpreted. Ocean acoustics is a field filled with confounding variables. Sound can reflect off layers of water, refract through temperature gradients, and distort as it travels over vast distances. A noise recorded in the trench may have originated hundreds or thousands of kilometers away, altered so thoroughly by its journey that its source becomes unrecognizable. Equipment itself can introduce artifacts, subtle resonances created by pressure or movement that mimic external signals. Even the animals we think we understand can surprise us, producing calls that vary by region, context, or behavior. Because of this, uncertainty is treated not as a failure, but as an expected part of listening in such an extreme environment. When an unexplained sound appears, the first assumption is not that it represents something extraordinary, but that it represents something not yet fully understood. This restraint is deliberate. The history of deep-sea exploration is filled with examples of early speculation later replaced by mundane explanations. Sounds once thought to be evidence of unknown creatures have been traced back to ice cracking under pressure, or to the interactions between currents and seafloor features. What makes the remaining anomalies interesting is not that they defy explanation entirely, but that they resist easy classification even after careful analysis. Some of the most discussed recordings consist of short, multi-part calls, sequences of tones that shift abruptly in frequency and texture. They do not resemble the long, sweeping songs of large whales, nor the sharp clicks of echolocation. They occupy a middle ground, complex enough to suggest intent, but ambiguous enough to defy confident attribution. In a few cases, researchers have proposed that these sounds may represent unfamiliar variations of known species, regional dialects or behaviors that have simply never been observed directly. The deep ocean, after all, is not a uniform space. It is divided by ridges, trenches and currents that can isolate populations for millennia, allowing communication styles to diverge in ways we're only beginning to document. Other sounds are even harder to place. Metallic-sounding vibrations, for example, have sparked quiet debate, not because they suggest machinery or artificial structures, but because their timbre does not easily match natural processes we commonly observe. Rock fracturing under pressure usually produces sharp, broadband noise. Biological sounds tend to have smoother contours shaped by anatomy. These metallic twangs sit awkwardly between categories, too clean to dismiss outright, too inconsistent to define. In the absence of visual confirmation, they remain unresolved. Importantly, scientists resist filling these gaps with speculation. there is a recognition that the deep ocean is not obligated to make sense on our terms. The trench does not owe us clarity. Instead, these sounds are catalogued, compared, and revisited as new data becomes available. Over time, many mysteries shrink as understanding grows. Others persist, not because they are extraordinary, but because the environment itself limits how much information can be gathered. This restraint stands in contrast to the way the human mind responds to the unknown. When we hear a sound without seeing its source, especially in a place we already perceive as alien, imagination naturally expands to fill the void. Scale becomes exaggerated. Intent is projected where none may exist. A faint, distant noise can feel enormous when stripped of context. This psychological response is ancient and deeply ingrained. For most of our evolutionary history, unseen sounds signaled potential danger. In the dark, the inability to identify a source was often more unsettling than the source itself. The trench amplifies this effect. It is a place defined by invisibility. Nothing can be seen without artificial light, and even then vision is narrow and incomplete. When a sound emerges from that darkness, detached from any visible reference point, it becomes a canvas for the imagination. This is why stories of the deep so often drift toward the idea of something large and hidden. It is not that the data suggest giants lurking in the abyss, but that the human mind is uncomfortable with ambiguity on such a scale. The unknown feels easier to manage when given a shape, even an imagined one. Yet the true strangeness of these unexplained sounds lies not in what they might represent, but in what they reveal about our relationship with the unseen. They highlight how much of our understanding depends on sight, and how disoriented we become without it. In the trench, listening replaces looking, and listening is an imprecise sense. It captures presence without form, activity without context. Known sounds remind us that the deep ocean is connected to the rest of the planet, constantly influenced by forces both natural and human. Unknown sounds remind us that connection does not equal comprehension. There are layers of activity occurring beyond our current ability to interpret them fully. As the recordings continue, as hydrophones remain patiently suspended in the darkness, the trench keeps listening, collecting echoes without judgment or narrative. Some will eventually be explained, folded into the growing body of knowledge about the deep. Others may remain unresolved, not because they hide something extraordinary, but because the environment itself refuses to yield complete answers. And it is in that space, between what we can identify and what we cannot, that the imagination naturally drifts toward size, toward presence, toward the idea that something vast must be responsible. As the mind lingers on unexplained sounds, it tends to reach for familiar shapes to make sense of them, and in the modern imagination there is one shape that rises again and again whenever the deep ocean is mentioned: a shadow with teeth, a survivor from a vanished age. The idea that something enormous, something ancient, still moves through the deepest water, hidden only because we've not looked closely enough. The name changes depending on the story being told, but the image remains remarkably consistent. A giant predator, fast, powerful, built to hunt, lingering just beyond the edge of human awareness. It is an idea that feels almost inevitable when we think about darkness and depth together. Yet when this image is held up against what we actually know about the trench, it begins to quietly fall apart. Not with drama or dismissal, but with the slow, methodical logic of biology. The Mariana Trench is not a place of abundance. It is not a rich hunting ground filled with large prey, moving freely through open water. It is instead one of the most energy-poor environments on the planet. Food arrives there slowly and unpredictably, drifting down from the surface in the form of tiny particles, fragments of dead organisms, or the occasional larger fall that may come only once in decades. For a massive warm-bodied predator to survive, it would require an enormous and constant supply of energy. Warm-blooded animals burn calories rapidly just to maintain their internal temperature. They must eat frequently, and they must eat well. The deep ocean offers neither. The water is cold, often just above freezing, and it remains that way year-round. Any large predator adapted to the surface would face a relentless drain on its energy reserves, with no reliable way to replenish them. Even if such a creature could tolerate the pressure, which is itself unlikely, it would slowly starve. The trench does not reward speed or power, it rewards patience and efficiency. This realization reframes the idea of giants in the deep. The problem is not that the ocean lacks large creatures, it is that we have been imagining the wrong kind of large. Down here, evolution has followed a different path, one shaped not by competition and chase, but by scarcity and time. This is where the phenomenon known as deep-sea gigantism quietly takes hold. It is one of the stranger patterns in marine biology, and one that seems almost counterintuitive at first. In the shallow ocean, many animals remain small. Crustaceans scuttle along the seafloor the size of a fingernail. Worms thread through sediment barely visible to the naked eye. But descend into the deep, and some of these same lineages appear again, transformed. Amphipods, distant relatives of tiny beach hoppers, grow to the length of a human forearm. Isopods, cousins of the small pill bugs found under rocks, become broad, armoured creatures the size of dinner plates. These are not monsters in the cinematic sense. They do not move quickly. They do not hunt aggressively. They drift, crawl, and wait. Their bodies are pale, often translucent, their movements slow and deliberate, conserving energy in an environment where every calorie matters. The reasons for this gigantism are still debated, but the leading ideas share a common theme. In the deep ocean, cold temperatures slow metabolism. Chemical reactions take longer. Growth happens gradually, stretched out over years or even decades, without the intense seasonal pressures of the surface, where predators, competition, and environmental changes constantly force adaptation. Deep-sea organisms may simply keep growing. There is no urgent signal telling them to stop. A larger body can also be an advantage in a place where meals are rare. Size allows for greater energy storage, larger reserves of fat that can sustain an animal through long periods of scarcity. When food does arrive, often in the form of a sinking carcass or a sudden pulse of organic matter, larger organism can consume more at once and endure longer afterward. These giants of the deep are not rulers of a bustling kingdom. They are survivors of a slow, quiet economy built on waiting. Their presence challenges our expectations. They show that the trench does not harbour the fast, aggressive hunters of popular imagination, but something stranger and, in its own way, more alien. Life here is not about dominance. It is about endurance. Even the largest creatures move with restraint, shaped by an environment that punishes excess. The deeper we look, the clearer this pattern becomes. Hard shells give way to softer bodies. Speed gives way to efficiency. Colour fades. Everything unnecessary is stripped away. The trench favours forms that can exist at the edge of possibility. Creatures that have learned not to fight their surroundings, but to become part of them. This understanding shifts the question from what might be hiding in the darkness to how anything manages to exist there at all. The giants of the deep are not relics of a lost world. They are products of a present one, sculpted by pressure, cold, and time into forms that feel unfamiliar precisely because they do not follow the rules we know. And yet, for all this knowledge, there remained for a long time a sense that we were still guessing from a distance. We could listen, we could map, we could send down instruments and retrieve data. But to truly understand what the deepest parts of the ocean were like, to move beyond speculation and indirect evidence, there was only one option left. Someone would have to go down there. The idea of truly knowing the trench had hovered at the edge of science for decades, tempting and impractical at the same time, until one cold morning in January of 1960, when that distance between curiosity and commitment finally closed. By then, the outlines of the challenge were clear. No camera lowered on a cable could offer more than a fleeting glimpse. No instrument package could feel what it meant to be there. If the deepest part of the ocean was ever going to be understood as a place rather than an abstraction, it would require a human presence, however brief, at the very bottom. The vessel chosen for that attempt was called Trieste, and its design reflected the sheer audacity of the task. It was not sleek or fast. It did not resemble the submarines people imagine today. Instead, it looked almost improvised, a strange hybrid of simplicity and stubbornness. A massive float filled with gasoline, chosen not for fuel but because it was lighter than water and nearly incompressible, provided buoyancy. Beneath it hung a single steel sphere, thick-walled and barely large enough to hold 2 men. This sphere was the only thing standing between human life and the crushing weight of nearly 11 kilometers of ocean. Inside that confined space sat Jacques Picard and Don Walsh, surrounded by gauges, dials, and the constant knowledge that no one had ever been where they were going. As Trieste began its descent, the surface world faded quickly. Light dimmed and then disappeared entirely. The blue glow of the upper ocean gave way to blackness so complete that it felt less like darkness and more like absence. Outside the small viewport there was nothing to see. Inside there was very little to do. The descent was slow, taking hours, not because of caution, but because gravity itself was restrained by the density of the water. Time stretched. Minutes lost their meaning. The 2 men sat shoulder to shoulder, listening to the faint hum of systems designed to keep them alive. Conversation came and went, often replaced by long silences. There was no scenery to distract from the steady awareness of depth increasing meter by meter. With each passing hour, pressure built against the hull, pressing inward with a force that no human body had ever experienced directly. The sphere had been calculated to withstand it, tested and retested, but calculations are always cleaner than reality. Steel behaves differently under theoretical stress than it does under the relentless, uniform weight of the deep ocean. Picard and Walsh understood this. Their trust was not blind optimism. It was a careful acceptance of risk, grounded in engineering and tempered by the knowledge that once they passed a certain depth, there would be no rescue, no quick ascent if something went wrong. Isolation settled in not as fear, but as clarity. They were farther from any other human beings than anyone in history had ever been. Not horizontally across the planet, but vertically beneath it. Even astronauts orbiting Earth could look down and see continents, clouds, the familiar curve of home. Inside Trieste there was nothing but darkness beyond the glass and the quiet presence of pressure all around them. The descent continued. Instruments ticked steadily, recording depth and temperature. The water outside grew colder, denser. Every sound inside the sphere felt amplified, each small movement of metal or shifting of weight carrying a significance it would not have had on the surface. The men became acutely aware of the vessel itself, listening for anything out of the ordinary, any change in tone or rhythm that might signal a problem. Hours passed this way, suspended between surface and sea floor, between certainty and the unknown. Then, without warning, the silence broke. A sharp, unmistakable sound rang through the sphere, a loud crack that echoed through the steel walls and vibrated through the cramped interior. It was not a groan or a gradual strain. It was sudden, decisive, and deeply unsettling. In that instant, every calculation and assumption was called into question. The sound had come from outside, from somewhere in the structure that separated them from the ocean. Pickard and Walsh froze, instinctively scanning the instruments, watching for signs of catastrophic failure. At that depth, even a small breach would be fatal within moments. Seconds stretched unbearably long as they waited for alarms, for pressure changes, for water where it did not belong. Nothing happened. The gauges remained steady. The hull held. The sphere continued its slow descent as though the sound itself had never occurred. But the moment lingered. It was a reminder that the trench does not announce its challenges in advance. It does not escalate gently. It simply applies force without malice or intention until something gives. That sound marked a threshold, the point at which the descent ceased to be an experiment and became an encounter. The rest of the journey unfolded beneath its echo, a quiet question hanging in the dark about what else might reveal itself before the bottom was reached. The sound lingered long after it had passed, not because it repeated, but because nothing followed it. In the aftermath of that sharp crack, the most unsettling thing was the absence of any further reaction from the vessel itself. No alarms, no rush of water, no sudden change in pressure. The instruments remained steady, as if the ocean had merely tapped the hull and then withdrawn its hand. Later analysis would suggest that an outer, non-structural acrylic window had failed under the strain, a component never intended to bear the full force of the descent, but at the time there was no such reassurance. In that steel sphere, suspended miles beneath the surface, this sound marked a moment when theory gave way completely to reality. From that point on, Pickard and Walsh were no longer descending into a calculated environment. They were entering a place that had already tested them once, and could do so again without warning. The final stretch of the descent continued slowly, almost anticlimactically, until at last the instruments indicated that there was nowhere left to go. The Trieste settled gently onto the seafloor of the Challenger Deep, touching down in a place no human had ever reached before. There was no dramatic impact, no plume of debris visible through the viewport, only a subtle sense of arrival, a shift in motion that signalled the end of downward travel. Outside the sphere, the fine sediment of the trench floor stirred and then began to settle, drifting back into stillness. When the external lights were switched on, they carved a narrow cone of visibility out of the darkness, illuminating a world that had existed unchanged for millions of years. What they saw at first was simplicity itself, a flat, pale expanse of silt stretching beyond the limits of the light, smooth and undisturbed, like fresh snow that had never known a footprint. It was a scene so quiet and uniform that it almost reinforced the idea of emptiness, as though the trench floor were nothing more than a silent, lifeless plain. But then, within that small circle of light, something moved. Both men noticed it independently, a brief flicker against the pale background, subtle but unmistakable. It was not debris stirred by their arrival. It moved with intention. According to their later descriptions, it was a flat, fish-like creature, roughly a foot long, pale in colour, with a shape reminiscent of a flounder or sole. They reported seeing eyes, dark against its light body, turning briefly toward the light before it slowly swam away, disappearing back into the darkness beyond the beam. The sighting was brief, lasting only moments, but it left a deep impression. At the surface, the report carried enormous implications. If accurate, it suggested the presence of vertebrate life at the deepest point of the ocean, thriving under pressures long thought to be incompatible with complex skeletal structures. It challenged prevailing assumptions about biological limits, hinting that life might be more adaptable than anyone had imagined. The idea captured public imagination quickly, becoming one of the most enduring and debated moments in the history of deep-sea exploration. But as the years passed, the certainty surrounding that observation began to erode. No subsequent mission, human or robotic, has ever confirmed the presence of a similar fish at that depth. Cameras have scanned the seafloor repeatedly. Remotely operated vehicles have hovered where Trieste once rested. Samples have been collected, images analysed, hours of footage reviewed, yet no vertebrate fish has appeared again in the Challenger Deep. This absence has fueled a quiet controversy that persists to this day. Modern biology suggests there are good reasons to be sceptical. At extreme pressures, the chemistry of bone becomes problematic. Calcium carbonate structures struggle to form and remain stable. Proteins essential to nerve function and muscle movement become increasingly difficult to maintain. For these reasons, most known fish species are limited to shallower depths, where pressure, though intense, does not fundamentally disrupt their biology. Below a certain threshold, invertebrates dominate, organisms without rigid skeletons, whose soft bodies can adapt more readily to compression. Critics of the Trieste sighting argue that what Picard and Walsh saw was more likely an invertebrate, perhaps a sea cucumber or similar organism, flattened and pale, moving in a way that could momentarily resemble a fish to observers already under immense psychological strain. The conditions inside the sphere, cramped, silent, and heavy with tension, could have influenced perception. After hours of darkness and the shock of the hull crack, even experienced explorers were not immune to misinterpretation, and yet the men themselves never wavered. They maintained that they knew the difference between a fish and a sea cucumber, that the movement they observed was deliberate and unmistakably Piscine. Their confidence adds another layer to the mystery, not because it proves the sighting, but because it resists easy dismissal. It leaves open the possibility that the trench briefly revealed something that has since remained hidden, either because it is extraordinarily rare, or because our methods of observation are still too limited. The trench does not offer repeated demonstrations on demand. It reveals things on its own terms, often fleetingly, and then closes itself again. Over the decades, the reported fish has become a kind of ghost in the scientific record, a single data point that cannot be replicated, neither fully accepted nor conclusively disproven. It occupies an uncomfortable space between observation and belief, reminding researchers that even direct human experience is not immune to uncertainty when it occurs at the very edge of possibility. Whether the sighting was a misidentification or a genuine glimpse of an organism uniquely adapted to the deepest pressures on Earth, its legacy is the same. It marked the moment when the trench shifted from an abstract extreme to a place where something unexpected might move just beyond the reach of light, visible only once and then never again. More than half a century passed after Trieste before another human returned to that exact depth, and when it finally happened, the context had changed in ways both subtle and profound. Technology had advanced, materials had improved, and our understanding of the ocean had grown. But one element of the journey had become even more stark. This time, there would be no companion. The descent would be made alone. In 2012, a single pilot sealed himself into a narrow vertical capsule barely wide enough to sit upright, knees drawn close, shoulders brushing the curved interior. The vessel was called Deep Sea Challenger, and unlike the buoyant balloon-like Trieste, it was designed to fall streamlined and dense, dropping through the water column with controlled urgency. As the capsule detached from the surface and began its descent, the last traces of daylight faded quickly, replaced by the same featureless black that had greeted Picard and Walsh decades earlier. But the psychological experience was fundamentally different. There was no shared silence, no exchange of glances, no quiet reassurance of another presence breathing nearby. The pilot was alone with the sound of his own respiration and the soft, constant hum of life support systems. The capsule was so small that there was no room to stretch, no way to change position meaningfully. Hours passed with the body held in a fixed posture, suspended in a vertical tube of steel and composites, surrounded on all sides by a force capable of erasing that space instantly if anything failed. As depth increased, external references disappeared completely. There were no stars to look at, no horizon, no sense of motion beyond instrument readings. The descent was measured not by sight, but by numbers ticking steadily upward, depth increasing metre by metre, pressure accumulating invisibly against the hull. In this isolation, time behaved strangely. Without visual change, minutes stretched and compressed unpredictably. The mind wandered, sometimes focusing intently on small details, sometimes drifting into abstract thought. The pilot later described the feeling not as fear, but as a kind of profound solitude, an awareness of being separated not just from other people, but from the entire human world. Even astronauts in orbit maintain a visual connection to Earth, a constant reminder of home. Here, there was nothing to look at, nothing to orient to. The environment offered no acknowledgement of the descent. It did not resist visibly. It did not respond. It simply was. As the capsule passed deeper, the sense of indifference grew. The trench did not feel hostile in an active way. There was no impression of threat or welcome. There was only the steady presence of pressure and darkness, a reminder that this place had existed long before human curiosity and would continue unchanged long after it. The pilot became acutely aware that survival depended entirely on engineering and preparation. There would be no improvisation at that depth, no external assistance, no second chances. The capsule either worked as intended or it did not. This clarity stripped the experience of drama, leaving something quieter and more unsettling in its place. The environment did not care whether he was there. It did not react to his presence in any way that could be perceived. Eventually, after hours of descent, the numbers reached their maximum and the capsule slowed, then settled onto the seafloor of the Challenger Deep. The moment of arrival was subtle, almost anticlimactic. There was no jolt, no dramatic plume visible outside. The fine sediment stirred gently and then drifted back down, settling into stillness. When the external lights switched on, they illuminated the same pale, silty plain described decades earlier, a landscape so simple it felt almost abstract. The trench floor stretched out in every direction, flat and undisturbed, offering no landmarks, no sense of scale beyond the limits of the light. In that moment, the loneliness of the descent sharpened into something else, This was not just isolation from people, it was isolation from context. The pilot was present in a place that did not reference anything else. There were no familiar shapes, no signs of life at first glance, no movement to anchor attention. It was as though the environment existed entirely for itself, complete and indifferent, with no need to acknowledge the observer within it. The feeling was described later as philosophical rather than emotional, a recognition of how small and temporary human presence is when placed against geological time and planetary processes. And then, as the light scanned the seafloor more carefully, something appeared that reframed the entire experience. It was not a dramatic discovery, not a new species or a geological marvel. It was something far more familiar, and because of that, far more unsettling. There, resting on the deepest floor of the ocean, in a place that had resisted human entry for all of history, was a simple piece of human debris, a plastic bag. It lay motionless on the silt, its shape unmistakable, its presence impossible to ignore. In that instant, the meaning of the descent shifted. The loneliness of the journey, the sense of being utterly removed from the human world, collided with the realization that the human world had arrived here long before he had. Not through intention or exploration, but through neglect. The trench, which had seemed so remote and untouched, revealed itself as already marked. The environment's indifference was not just a human presence, but a human impact. The plastic had drifted down slowly, carried by currents, sinking over weeks or months until it reached this deepest place and settled quietly. It required no engineering, no courage, no risk. It simply fell. This discovery reframed the trench not as a pristine frontier awaiting exploration, but as a mirror reflecting the reach of human activity. The isolation felt during the descent was real, but it was no longer absolute. The deepest place on Earth was not beyond our influence. It was already part of our story, whether we intended it or not. The realization that human debris had reached the deepest place on Earth before most humans ever could carries a quiet weight that does not fade quickly. A plastic bag resting on the floor of the Challenger Deep is not shocking because plastic exists or because pollution is new, but because of the way it arrived. There was no deliberate journey, no expedition, no technological triumph involved. It simply drifted. Somewhere far above, perhaps thousands of kilometers away, a lightweight object entered the ocean, whether dropped accidentally or discarded without thought. From there, gravity and time did the rest. Ocean currents carried it slowly across basins, and when those currents weakened, the bag began to sink, descending through layers of water, passing through sunlight, twilight, and complete darkness, until it finally settled into a place defined by pressure and silence. This process required no intention. It followed the same physical laws that govern everything else in the ocean. That is what makes it unsettling. The trench did not resist the plastic. It accepted it as it accepts everything that falls long enough and far enough. Over time, explorers and robotic vehicles have found more than just a single piece of debris. Wrappers, fragments of synthetic fibers, traces of chemicals, even microscopic plastic particles embedded in the sediment have been documented in Hadal environments. These materials do not break down the way organic matter does. They persist, slowly fragmenting into smaller pieces but never truly disappearing. The trench, once imagined as a final untouched frontier, begins to look less like a sanctuary and more like a record keeper. Everything that sinks eventually arrives somewhere, and the deepest places become natural collection points. The shape of the trench matters here. Its steep walls and immense depth create a kind of gravitational funnel. Material that falls into it is unlikely to escape. Currents at that depth are weak and sluggish. There is little energy to lift objects back out. What arrives tends to stay. In this sense, the trench does not merely receive explorers or drifting debris, it traps them. This trapping effect extends beyond visible trash. Chemical pollutants, heavy metals, and other industrial byproducts introduced into the ocean at the surface can bind to organic particles and sink over time, becoming part of the fine sediment that blankets the trench floor. Studies have found elevated concentrations of certain contaminants in Hadal organisms, evidence that even the simplest life forms at the bottom are not isolated from surface activity. These creatures ingest sediment as part of their feeding process, absorbing whatever has settled there along with their nutrients. The impact is slow and subtle, unfolding over decades rather than years, but it is real. The idea that the trench might serve as a final dumping ground was once viewed almost as a solution. Out of sight, out of mind. The vastness of the ocean was assumed to be capable of diluting anything we introduced into it. But dilution does not mean disappearance. In the deepest parts of the sea, there is nowhere left for material to spread. Instead, it accumulates. The emotional weight of this realization comes not from alarm but from contrast. For much of its history, the trench represented the ultimate unknown, a place beyond reach, beyond influence. It was imagined as pristine not because anyone had verified that, but because its inaccessibility made it convenient to believe. The discovery of trash there collapses that belief quietly and completely. It reveals that there are no absolute boundaries between human activity and the rest of the planet. Even the most remote environments are connected by processes that operate slowly but relentlessly. The trench stops feeling like a separate world and starts to feel like a mirror held up to our own. This does not mean the trench is ruined or devoid of value. It means its story is more complicated. It is no longer just a destination for explorers or a laboratory for scientists. It is a place where the consequences of surface life become visible in their final form. The plastic bag at the bottom is not dramatic. It does not glow or move or announce itself. It simply rests there, unchanged, a quiet marker of how far human influence extends without effort. This changes how we think about exploration. The first humans who reached the bottom did so with enormous risk, relying on careful engineering and personal courage. Their presence was temporary, fleeting. The debris, by contrast, arrived effortlessly and may remain for centuries. In that comparison, the trench feels less like a place we visit and more like a place we leave things behind. It becomes a repository not just of sediment and biological remnants, but of choices made far above, often without awareness of where they might lead. This understanding reframes the deep ocean not as an empty abyss waiting to be discovered, but as an active participant in planetary systems, absorbing and recording the byproducts of life at the surface. The trench does not judge what it receives. It does not distinguish between a whale fall and a plastic bag, between natural debris and manufactured waste. It treats them all the same, subjecting them to pressure, darkness, and time. In doing so, it reveals something uncomfortable but important. Our impact does not stop where our presence ends. It continues quietly, following the same physical laws that shape the rest of the world, sinking steadily until it reaches the deepest places we once believed were beyond our reach. Seen from above, the trench looks like a wound, a long, narrow scar cut into the surface of the planet, but that image is misleading in a subtle way. Wounds suggest damage that needs to be healed. The Mariana Trench is not damage. It is a function. It exists because the Earth is not finished, not static, not content to remain as it is. Beneath the oceans and continents, the planet is constantly moving, reshaping itself with a patience that dwarfs human time. The trench is one visible expression of that motion, a place where the Earth is actively recycling its own surface. To understand it, you have to let go of the idea of solid ground as something permanent and instead imagine the crust as a collection of enormous, slowly drifting plates, each one carrying oceans and continents as if they were cargo. These plates move so slowly that their motion is imperceptible in a human lifetime, advancing at roughly the speed your fingernails grow, a few centimeters a year, almost nothing, and yet, given enough time, that almost nothing becomes everything. The Mariana Trench marks the boundary between two of these plates. To the east lies the Pacific Plate, one of the largest and oldest pieces of crust on Earth. To the west is the Philippine Sea Plate, younger, smaller, and riding slightly higher. As these two slabs of lithosphere creep toward one another, the denser Pacific Plate does not collide head-on in a dramatic crash. Instead, it bends, it yields, it begins to slide beneath the Philippine Sea Plate, angling downward into the hot ductile mantle below. This process is known as subduction, and it is one of the primary ways the planet renews itself. Old crust is consumed, melted, and eventually reborn as magma that may surface elsewhere as new volcanic rock. The trench is the surface expression of this descent, the visible crease formed as one plate is dragged down into the interior of the Earth. This is not a clean or gentle process. The Pacific Plate does not glide smoothly into the mantle like a sheet slipping under a door. It scrapes, it fractures, it resists. As it bends downward, it pulls on the edge of the overlying plate, dragging it down and creating that deep, narrow trough in the seafloor. The trench is therefore not empty space. It is a place of immense stress, where rock is under tension, compressed, twisted, and slowly destroyed. Every year, as the plates continue their almost imperceptible movement, the trench deepens by fractions of a millimeter, extending the planet's recycling system one tiny step further. Over millions of years, those fractions accumulate into kilometers. This perspective reframes the trench entirely. It is not a passive hole waiting to be explored. It is an active machine, powered by the internal heat of the Earth, grinding away relentlessly at the crust. The sediment that settles on its floor, the debris that falls into it, even the water above it, are all part of a dynamic system shaped by forces far older than any ocean creature or human artifact. The trench is a boundary, not just between plates, but between states of matter, where cold, brittle rock gives way to hotter, more plastic material below. As the subducting plate descends, it carries with it everything that has accumulated on its surface. Layers of sediment, trapped seawater, organic material, even chemical signatures of life. These materials are dragged downward, subjected to increasing heat and pressure, triggering chemical reactions that release fluids and gases into the surrounding mantle. Some of these fluids rise back toward the surface, fueling volcanic arcs nearby. Others alter the chemistry of the mantle itself, influencing how magma forms and behaves. In this way, the trench is not just swallowing the surface, it is feeding the planet's interior with information about what has existed above. This slow movement of plates also explains why the trench is so deep and narrow compared to other features. It is not being carved by erosion in the way a canyon is carved by a river. It is being pulled open from below, stretched and depressed by the weight and motion of an entire slab of oceanic crust. This makes it structurally unstable in ways that are difficult to visualize. The rocks along the trench walls are fractured and faulted, riddled with weaknesses that can slip suddenly when stress becomes too great. These slips are not always dramatic at the surface, but deep within the earth they can be violent, releasing energy in the form of earthquakes that originate hundreds of kilometers down, far deeper than most seismic activity. The trench, then, is not just a record of motion, it is a source of it. It is one of the places where the planet releases the tension created by its own slow movement. And yet, despite this constant activity, the surface appearance of the trench floor is deceptively calm. Sediment settles, life adapts, debris accumulates, everything about it feels still, almost timeless. This contrast between appearance and reality is part of what makes the trench so compelling. Beneath that quiet, pale silt lies a conveyor belt of destruction and renewal, operating on scales of time that make human history feel like a brief interruption. The Earth is not violently tearing itself apart here. It is methodically reworking itself centimetre by centimetre, year by year, and this motion, slow as it is anything but gentle. The grinding contact between plates builds stress continuously, storing energy until it is released in sudden, unpredictable ways. The trench may look serene, but it is the surface expression of a powerful, ongoing process that reshapes the planet from the inside out. The grinding motion beneath the trench does not release its energy smoothly or predictably, and this becomes most apparent when the Earth does something that, by our own rules, it should not be able to do. Earthquakes are familiar to us as shallow events, fractures in brittle rock near the surface where plates scrape past one another or pull apart. In those environments, rock behaves in a way that makes sense to our intuition. It is cold enough to snap, rigid enough to store tension, and when it fails, it does so suddenly. But beneath the Mariana Trench, earthquakes occur at depths so great that rock should no longer be able to break at all. These are known as deep focus earthquakes, and they originate hundreds of kilometers beneath the surface, far below the level where conventional geology says fracturing should be possible. At those depths, pressure and temperature are immense. Rock is expected to deform slowly, to flow like thick putty rather than shatter like glass. And yet, seismic instruments around the world routinely record tremors rising from these impossible depths, their signatures unmistakable, their energy real. For decades, this presented a fundamental contradiction. How could something break when it should only bend? The trench sits above one of the most active regions for these deep focus events, making it a natural laboratory for a mystery that forces scientists to rethink the behavior of the planet's interior. The answer, it turns out, is not a single mechanism, but a collection of processes layered on top of one another, each subtle on its own, but powerful in combination. As the Pacific Plate descends beneath the Philippine Sea Plate, it does not immediately lose its identity. For hundreds of kilometers, it remains cooler than the surrounding mantle, carrying with it minerals and structures formed at the surface. These minerals contain water locked into their crystal structures, water that does not exist as liquid but as part of the rock itself. As the plate sinks deeper, pressure and temperature increase, and those minerals begin to change. Their crystal structures rearrange, squeezing out the trapped water. This release acts like a lubricant in some places, reducing friction, but in others it creates zones of instability. The sudden movement of fluids can weaken rock locally, allowing it to fail abruptly, even in an environment where slow deformation should dominate. In addition, The minerals themselves undergo phase changes, transformations where their atomic arrangements shift into denser forms. These changes are not always gradual. In some cases, they happen suddenly, producing sharp reductions in volume that generate stress faster than the surrounding material can absorb it. The result is a sudden release of energy, an earthquake born not of simple fracture, but of transformation. Stress also accumulates mechanically. The descending plate is not free to slide smoothly. It bends and flexes as it sinks, storing elastic energy over long periods. Portions of it may become temporarily locked against the surrounding mantle, resisting motion until the accumulated stress overwhelms that resistance. When it finally gives way, the release propagates as seismic waves, travelling upward and outward through the earth. These deep earthquakes are often too far below the surface to be felt directly, but they matter because of how they interact with shallower structures. The energy they release does not simply disappear, it moves. In some cases, deep tremors can transfer stress upward, triggering shallower faults closer to the surface. When those faults slip, the consequences become much more immediate. The trench is particularly important in this chain of events because it sits beneath massive columns of water. When shallow sections of the subduction zone rupture, the seafloor can move vertically by several meters in seconds. This sudden displacement pushes against the water above it, lifting or dropping entire sections of the ocean surface. The water does not have time to adjust gradually. Instead, it radiates outward as a series of long, low waves that travel across the ocean basin at jetliner speeds. These are tsunamis, and while they may pass almost unnoticed in deep water, they grow dramatically as they approach shallow coastlines, where their energy is compressed into towering walls of moving water. In this way, energy released deep beneath the trench can ultimately reshape coastlines thousands of kilometers away. What begins as a subtle mineral transformation or stress release deep in the earth can end as one of the most destructive natural events humans experience. And yet, even here, violence is not the only outlet. The trench is not simply an engine of sudden catastrophe. Much of the energy generated by subduction escapes quietly. Heat flows upward through the crust. Fluids seep out slowly through cracks and vents. Stress is relieved incrementally through tiny, almost imperceptible movements that never register as earthquakes at all. The Earth is constantly negotiating with itself, releasing pressure in ways that range from explosive to almost tender. This dual nature is part of what makes the trench so difficult to characterize. It is both a site of extreme violence and a place of profound patience. It can remain still for decades, accumulating stress silently and then release it in seconds. Or it can leak energy continuously, reshaping chemistry and temperature without drawing attention. The deep focus earthquakes challenge our assumptions not just about geology, but about predictability. They remind us that the planet does not always behave according to simplified models. Conditions change with depth in ways that create entirely new behaviors, new rules that only reveal themselves when we listen carefully enough. Beneath the apparent calm of the trench floor, the Earth is alive with motion, some of it sudden and dramatic, some of it slow and subtle, all of it part of a system that has been operating for billions of years. And not all of that energy announces itself with a jolt. Some of it slips out quietly, reshaping the deep ocean in ways that are easier to miss but no less important. The same forces that grind plates together and release energy in sudden earthquakes also allow something far more gradual and intimate to happen, a slow exchange between the deep interior of the planet and the cold darkness of the ocean above. In certain places along the trench and the surrounding volcanic arc, the crust is thin enough, fractured enough, that seawater can seep downward through cracks in the rock. This water does not simply pool and return. It descends for kilometers, carried by gravity into regions where the Earth's internal heat becomes impossible to ignore. As it sinks, the water is compressed, heated, and chemically transformed until it becomes something no longer recognizable as ordinary seawater. Temperatures climb past the boiling point, not to a gentle simmer, but to extremes that would vaporize water instantly at the surface. 400 degrees Celsius, hot enough to melt lead. Yet at these depths, under immense pressure, the water cannot boil. It remains liquid, dense, and highly reactive. As it circulates through the hot rock, it strips minerals from its surroundings, dissolving metals like iron, copper, zinc, and sulfur into a superheated acidic solution. This altered fluid then begins its slow return toward the seafloor, driven upward by buoyancy and pressure, following the same fractures that carried it down. When it finally emerges back into the ocean, it does so violently, jetting out of the crust through chimney-like structures that can rise several meters above the seabed. To an observer, the scene looks dramatic, almost volcanic. Thick, dark plumes billow upward from these vents, twisting and expanding as they mix with the near-freezing seawater around them. This is where the term black smoker comes from, but the description is deceptive. What looks like smoke is not smoke at all. It is a cloud of microscopic mineral particles instantly precipitated out of solution as the superheated fluid meets cold water. The minerals solidify in mid-flow, creating a dark, shimmering plume that rises and then disperses, slowly settling back onto the seafloor. Over time, this process builds the chimneys themselves, layer upon layer of deposited minerals accumulating around the vent opening, forming intricate, fragile structures that are constantly growing, collapsing, and rebuilding. These vents are not rare curiosities. They are part of a global system, scattered along mid-ocean ridges and subduction zones wherever the conditions are right. In the context of the trench, they represent places where the planet's internal heat escapes not through explosive eruptions, but through steady leakage. Heat that has been trapped deep within the Earth for billions of years finds a path upward, carrying with it chemical information from the mantle and lower crust. The water that emerges is not just hot, it is fundamentally altered, its chemistry dominated by substances toxic to most surface life. Sulfides, heavy metals, acids. By any conventional measure, these vents should be sterile. No sunlight reaches them. The water pouring out is lethally hot and chemically hostile. And yet, when the first cameras reached these environments, they did not find emptiness. They found abundance. Around the bases of the chimneys, clinging to the rock and crowding into every available crevice, were living communities unlike anything previously known. Tube worms taller than a human stood packed together in dense clusters, their white chitinous tubes anchored to the seafloor. They had no mouths, no digestive systems. Instead, their survival depended on an internal partnership with bacteria living inside their tissues. These bacteria used the chemical energy in the vent fluids, particularly hydrogen sulfide, to produce organic molecules through a process called chemosynthesis. It was a revelation. Life here was not powered by sunlight, not dependent on photosynthesis, but fueled directly by the Earth's internal chemistry. Around the tube worms were fields of clams and mussels, their shells gaping slightly as they filtered vent-influenced water. blind crabs scuttled across the mineral-encrusted surfaces, navigating by touch and chemical cues rather than sight. Shrimp clustered so densely near the vent openings that they seemed to writhe. Their bodies adapted to tolerate temperature gradients that would kill most organisms instantly. The water just centimeters away from a vent could be near freezing, while the fluid emerging from the opening remained superheated. Life here existed on a knife edge, exploiting narrow zones where conditions were just survivable. The discovery of these ecosystems forced a fundamental re-evaluation of what life needs to exist. For centuries, the assumption had been that sunlight was the ultimate energy source for all complex life on Earth. Plants captured it. Animals ate plants, or ate animals that ate plants. The deep ocean was thought to be a desert sustained only by scraps falling from above. Hydrothermal vents shattered that idea. Here was a complete ecosystem, from primary producers to top consumers, operating entirely independent of the sun. The energy came from below, from the planet itself. This realization carried implications far beyond marine biology. It suggested that life might not be limited to Earth-like conditions bathed in starlight. If organisms could thrive in darkness, fueled by chemical gradients and geothermal heat, then similar systems might exist elsewhere in the universe. The trench and its vents became more than a geological curiosity. They became a model for how life could arise and persist in environments once thought utterly inhospitable. But even as scientists marveled at this resilience, the vents themselves remained unstable and temporary. Chimneys grow, collapse, and shift as mineral deposition changes flow paths. Entire vent fields can shut down as the underlying heat source moves or diminishes. Life adapts, colonizes, and abandons these sites in cycles measured in years and decades, not millennia. The trench floor, which seems so still and timeless, is punctuated by these fleeting oases of energy, places where heat leaks out and life gathers briefly before moving on. This constant turnover reinforces the sense that the deep ocean is not static. It is dynamic in ways that are easy to overlook because they unfold slowly or far from view. The vents do not roar or erupt dramatically most of the time. They whisper heat into the water, carrying the planet's inner energy upward in steady streams, and against all expectation, life listens. It settles in, adapts, and flourishes, proving again that the conditions we label as impossible are often only impossible by the standards of the surface world. As the heat leaks upward and chemistry takes over where sunlight never reaches, another transformation quietly unfolds, one that feels less like biology or geology and more like the planet bending its own rules. The pressure that defines the trench does more than crush and confine. It changes the very states of matter, allowing conditions that feel almost impossible from a surface perspective. Down here, substances behave in ways that seem to contradict intuition, built in a world of air and moderate force. Gases that should expand and disperse are instead forced into liquid form. Reactions that would never occur at the surface become not only possible but stable. Physics, it turns out, is not broken in the trench, but rewritten under a different set of constraints. One of the most striking examples of this occurs near certain vent systems associated with the trench, where researchers have observed something that looks, at first glance, like a mistake. Shimmering bubbles rising slowly, from the seafloor drifting upward with the gentle grace of carbonation in a glass. But these are not bubbles of gas, they are liquid. In these extreme conditions, carbon dioxide, a gas we exhale without thought, exists as a dense flowing liquid. The pressure is so great and the temperature so low that CO2 crosses a threshold it can never reach at the surface. It pools in depressions, seeps from cracks, and rises in slow, pearlescent streams that defy expectation. The sight is unsettling, not because it is violent, but because it is calm. The liquid does not rush or explode. It behaves gently, almost delicately, as if unaware that it is violating assumptions formed over a lifetime. To witness this through the lens of a deep-sea camera is to watch a familiar substance adopt an alien personality. The bubbles do not burst. They glide. They accumulate. They dissolve into the surrounding water in ways that seem choreographed rather than chaotic. This is not a place where surface intuition applies. Pressure forces molecules closer together, alters electron behavior, stabilizes arrangements that would be fleeting or impossible elsewhere. Even water itself behaves differently. At these depths, it becomes more compressible, its density changing subtly with pressure in ways that affect sound, movement, and chemical interaction. The trench is not just deeper than the rest of the ocean, it is qualitatively different. It occupies a regime where small changes in depth can produce large changes in physical behavior. This is why instruments designed for shallower waters often fail here, not because they are poorly made, but because the assumptions embedded in their design no longer hold. Lubricants thicken or solidify. Seals behave unpredictably. Electronics respond differently as pressure alters the spacing between components at microscopic scales. Engineers working on Hadal exploration learn quickly that solutions borrowed from the surface must be reimagined entirely. Even time feels altered in these conditions. Chemical reactions slow, diffusion becomes more constrained. Processes that would be rapid elsewhere unfold gradually, stretching events over longer intervals. This contributes to the dreamlike quality of deep-sea footage. Movements appear deliberate, almost ceremonial. Particles drift instead of scatter. Plumes rise and curl with patience. Nothing seems hurried. The trench imposes a pace that life and matter alike must accept. This strangeness reinforces a crucial point. The trench is not simply a deeper extension of the ocean we know. It is a separate domain governed by the same fundamental laws, but operating under extremes that shift outcomes dramatically. What feels impossible at the surface becomes routine here. What seems stable above may be transient below. The environment demands adaptation not just in form, but in function, at levels so fundamental that they reshape chemistry itself. This realization feeds directly into how life manages to exist at all in these depths. Organisms here are not merely tolerant of pressure, they are dependent on it. Their proteins are structured to fold correctly only when squeezed. Their cell membranes maintain the right balance of fluidity only under immense force. Remove that pressure, and the systems unravel. In some cases, creatures brought rapidly to the surface do not survive long enough to be studied, not because they are crushed, but because they lose the pressure that holds their biology together. They soften, lose structural integrity, and effectively dissolve. This inversion is profound. Pressure, which we instinctively associate with danger, becomes a form of support. The trench is not hostile to life adapted to it. It is hostile only to life that assumes the surface rules apply everywhere. The surreal imagery captured near the trench, liquid gases flowing like slow rain, mineral plumes rising like smoke that never burns, organisms moving as if suspended in time, all point to the same conclusion. This is not just an extreme environment, it is a different one. Depth alone does not explain it. The combination of pressure, temperature, and chemistry creates a setting that feels almost experimental, as though the planet itself is testing alternate configurations of matter and life. The deeper scientists look, the more they realize that understanding the trench requires more than extrapolating downward from familiar conditions. It requires accepting that at a certain point, the rules we rely on are no longer sufficient. New baselines must be established, new expectations formed, and life, as it so often does, meets this challenge not by resisting, but by rewriting itself from the inside out. As these altered rules of matter and chemistry take hold, scientists draw a boundary not on a map but in understanding, a threshold beyond which the ocean stops behaving like the ocean we think we know. This region begins at roughly 6,000 meters below the surface and extends downward into the deepest trenches, and it has been given a name that reflects how alien it once seemed: the Hadal zone. Borrowed from Hades, the ancient underworld, the term was chosen not for drama but for accuracy. This is the realm where conditions cross from extreme into fundamentally incompatible with most known forms of life. Light has been gone for kilometers already, but here even pressure stops being a simple physical force and becomes a biochemical one. It presses not just on bodies, but on molecules, reshaping the machinery of life at its most basic level. For organisms evolved at the surface, this pressure is catastrophic in a quiet, methodical way. Cell membranes, which must remain flexible, enough to allow nutrients and signals to pass through, begin to stiffen. The lipid layers that form these membranes pack too tightly together, losing their fluidity. Proteins, whose function depends entirely on their precise three-dimensional shape, begin to misfold. Enzymes fail to latch onto the molecules they are meant to transform. Metabolic pathways slow, then stall. Nerve signals become erratic. Muscles lose coordination. Death, in this environment, does not arrive as a dramatic crushing, but as a cascade of microscopic failures, each one subtle, each one irreversible. This is why surface life cannot simply be armoured and sent downward. Even if a rigid shell could withstand the pressure mechanically, the biology inside would unravel. The Hadal zone does not tolerate compromise. It demands adaptation at every level, from the structure of DNA to the composition of cell fluids. The pressure also affects water itself, altering how molecules interact, how substances dissolve, how reactions proceed. Oxygen behaves differently. Carbon dioxide behaves differently. Even the simplest chemical gradients shift, forcing organisms to re-engineer how they harvest and use energy. For decades, these realities led scientists to assume that the Hadal zone was largely sterile, a place too punishing for complex life to exist. Early models predicted that only microbes might persist there, clinging to survival at the very edge of possibility. But as exploration improved and instruments became capable of enduring these depths, that assumption began to fracture. What researchers found was not absence, but specialization. Life had not avoided the Hadal zone, it had adapted to it with remarkable precision. Organisms living here do not resist pressure, they incorporate it. Their proteins are stabilized by special molecules that prevent misfolding under compression. Their cell membranes contain unique lipid compositions that maintain flexibility even when squeezed by thousands of atmospheres. Their metabolic processes are tuned to operate slowly and efficiently, conserving energy in a world where food is scarce and chemical reactions proceed at a different pace. These adaptations are not superficial. They are written into the organism's biochemistry, inherited and refined over countless generations. Remove these creatures from their environment, and the adaptations become liabilities. Without pressure, their proteins lose support. Their membranes destabilize. They cannot survive the conditions we consider normal. This inversion underscores how distinct the Hadal zone truly is. It is not simply the bottom of the ocean, it is a separate biological province with its own rules, its own constraints, and its own solutions. The Hadal zone also reshapes how time is experienced by its inhabitants. Growth is slow, reproduction is infrequent, lifespans may be long by surface standards, not because life is easy, but because everything happens gradually. Energy arrives, in trickles rather than floods. Organisms cannot afford waste. They wait. They endure. They make use of whatever arrives, whether it is a dusting of organic particles drifting down from above or a sudden rare bounty like a fallen carcass. This economy of patience defines the zone as much as pressure does. It is a world built on scarcity, where survival depends on being ready when opportunity finally appears. The Hadal zone forces a re-evaluation of what it means for an environment to be habitable. Habitability is not about comfort, it is about consistency. The trench is consistent in its hostility, unchanging in its pressure, temperature and darkness. For life that can align itself with those constants, the environment becomes stable, even predictable. The danger lies in change, not in extremes. This is why the trench can support specialized ecosystems even as it excludes nearly everything else. It is selective, not empty. This understanding reframes the earlier discoveries of sound, heat, and strange chemistry. They are not anomalies scattered through an otherwise lifeless abyss. They are features of a system that operates according to a different logic, one that surface intuition struggles to follow. The Hadal zone is not merely a depth classification. It is a reminder that Earth contains realms where familiar assumptions fail completely, where survival requires a rewriting of life's most basic instructions. And yet, within this underworld, within this place named for death, life does not merely persist. In its own quiet, patient way, it thrives. In the Hadal zone, where armor fails and rigidity becomes liability, one of the most effective predators looks almost unfinished, as though it were never meant to be solid at all. When cameras finally captured clear footage of Hadal snailfish drifting just above the trench floor, the reaction was not fear or awe, but confusion. These fish appear fragile, translucent, their bodies soft and gelatinous, lacking the heavy scales, dense bones, or powerful musculature we associate with survival in extreme environments. Their heads are oversized, their bodies tapering into thin, flexible tails, their skin pale and ghost-like against the dark water. By surface standards, they look defenseless, and yet they are among the highest living vertebrates ever confirmed at these depths, thriving where almost nothing else with a backbone can function. Their success lies precisely in what they lack. Hard armor, which seems protective at the surface, becomes a problem under immense pressure. Rigid structures resist compression unevenly, creating stress points that can fracture or fail. Soft tissues, by contrast, compress uniformly. They yield without breaking. The snailfish's body is composed largely of gelatinous tissue with a density close to that of the surrounding water, making it nearly neutrally buoyant. This means it does not have to fight gravity to stay suspended. It can hover effortlessly, conserving energy in a place where energy is precious. Its bones, such as they are thin and lightly mineralized, reducing the chemical problems associated with maintaining rigid skeletal structures under pressure. Even its muscles are adapted for slow, deliberate movement rather than bursts of speed. In the trench, chasing prey aggressively is inefficient. Food is scarce, and fast movement burns calories that may not be easily replaced. Instead, the snailfish drifts close to the seafloor, sensing vibrations and chemical cues, feeding primarily on small crustaceans like amphipods that are themselves adapted to the deep. These amphipods arrive in abundance when food falls from above, and the snailfish takes advantage of these moments, feeding steadily rather than frantically. At the biochemical level, the snailfish reveals just how deeply life has rewritten itself to exist here. Its cells contain high concentrations of molecules known as piezolites, substances that stabilize proteins under pressure. One of the most important of these is trimethylamine N-oxide, or TMAO, a compound that helps proteins maintain their proper shape when squeezed by thousands of atmospheres. Interestingly, TMAO is also present in surface fish, but at much lower concentrations. As depth increases, so does the amount of this molecule in the body, rising steadily until, at Hadal depths, it reaches levels that would be toxic to shallow water organisms. For the snailfish, however, this chemistry is not optional. It is the difference between functional proteins and biochemical collapse. The membranes of its cells are similarly specialized, composed of lipids that remain fluid under compression, allowing nutrients and signals to pass through even when pressure would normally lock those membranes into rigid states. These adaptations are so finely tuned that they bind the animal completely to its environment. If a Hadal snailfish is brought rapidly to the surface, the loss of pressure is catastrophic. The very molecules that stabilize its proteins at depth become destabilizing without compression. Cell membranes lose coherence. Tissues soften beyond structural integrity. The fish does not explode or rupture dramatically. It simply cannot maintain itself. This is why live specimens from the deepest trenches are almost never observed at the surface. What survives at depth cannot survive without it. This fact complicates our understanding of deep-sea life. Much of what we know about animals comes from direct observation, from studying them alive in controlled conditions. The trench denies us this approach. Its inhabitants are inseparable from the forces that shape them. They cannot be removed from their context without being destroyed. This forces scientists to rely on remote observation, genetic analysis, and careful inference, piecing together lives that unfold entirely beyond our physical reach. The snailfish also challenges our ideas about predation. In the surface ocean, predators are often defined by speed, power, and aggression. Teeth, jaws, streamlined bodies built for pursuit. In the trench, predation looks different. It is quiet, opportunistic. The snailfish does not dominate through force, but through compatibility. Its softness allows it to exist where others cannot. Its patience allows it to wait. Its sensory systems are tuned not to sight, which is useless here, but to subtle vibrations and chemical traces in the water. Hiding in this environment does not mean blending into colourful backgrounds or darting into crevices. It means becoming unremarkable, almost invisible, matching the density and movement of the water itself. The snailfish does not stand out against the trench floor. It drifts just above it, its pale body reflecting little light, its movements slow enough to escape notice. In a place where nothing is watching in the way surface predators watch, this form of invisibility is enough. The success of such a creature reinforces a broader truth about the trench. Survival here is not about resisting the environment. It is about aligning with it so completely that the distinction between organism and surroundings begins to blur. The softest predator thrives not despite the harshness of the Hadal zone, but because it has allowed that harshness to define it. And as we look closer at how hiding, hunting, and surviving work in this realm, it becomes clear that even the basic concepts of camouflage and defense must be reimagined in a world where pressure, darkness, and scarcity rewrite the rules entirely. In the world just above the trench floor, where the water is not only dark but fundamentally empty of reference, survival has taken an unusual turn. There are no reefs to hide behind, no forests of kelp, no rocks casting helpful shadows. It is an open volume of water under pressure so intense that even light behaves differently, scattering and vanishing almost as soon as it appears. In this place, many creatures have arrived at the same quiet conclusion through evolution. If you cannot hide behind something, the only remaining option is to remove yourself from view entirely, not by fleeing, not by fighting, but by erasing your own outline. Transparency becomes the most effective form of camouflage. It is a solution so counterintuitive that it feels almost philosophical. To survive, you do not become stronger or faster. You become less visible. The deep ocean is filled with animals that seem less like solid beings and more like ideas of animals, their bodies reduced to the bare minimum required to function. The telescope octopus is one of the most striking examples. Its body is almost completely clear, a soft gelatinous form that refracts the faintest hints of light passing through the water. What little structure it has appears suspended inside it, organs floating as if held in place by invisible threads. Its most defining features are its eyes, long tubular structures that extend upward like periscopes. These eyes are not designed to scan the seafloor or the darkness around it, but the space above. In the deep ocean, danger and opportunity most often come from above. Food falls, predators descend. The telescope octopus drifts slowly, almost motionless, its eyes fixed upward, watching for silhouettes that interrupt the faint glow filtering down from the distant surface. Its transparency ensures that when light does arrive, it passes through without casting a revealing shadow. Shadows, in this environment, are lethal. Even in darkness, bioluminescent flashes from predators or passing organisms can backlight a body, turning it into a visible shape. To be transparent is to deny that contrast. Other creatures have taken this strategy even further. Glass squid, for example, are so clear that at first glance they appear to be nothing more than drifting shapes in the water, distortions rather than animals. Their muscles, skin, and connective tissues are nearly invisible. Only their eyes and digestive glands remain opaque, and even those present a problem. Any solid structure risks giving away the animal's position when light hits it. Evolution's solution here is remarkably precise. These squid use bioluminescence not to attract attention, but to cancel it out. Along their bodies are tiny light-producing organs that emit just enough illumination to match the ambient light coming from above. When viewed from below, the squid's own light fills in the shadow that its opaque organs would otherwise cast. It is a form of active camouflage known as counter-illumination, a living invisibility cloak calibrated in real time. The squid is not glowing brightly, it is glowing just enough to disappear. This requires constant adjustment, a biological feedback loop that measures surrounding light levels and responds instantly. In the deep, where light is rare and precious, these creatures spend energy not to be seen, but to avoid being noticed. The result is an ecosystem populated by beings that are almost not there. They drift, hover, pulse gently, their movements slow and deliberate. Speed is unnecessary when you cannot be seen. Armor is irrelevant when there is nothing to strike. The pressure that would crush rigid shells instead supports these soft forms, holding them together like a constant embrace. Their bodies are often filled with watery tissues that match the density of the surrounding seawater, further reducing contrast and effort. They do not sink or float aggressively. They exist in balance. In this environment, invisibility is not just visual, it is behavioral. Many of these animals move so slowly that they create almost no disturbance in the water. Predators often rely on sensing pressure waves or vibrations. A sudden movement sends a signal through the water that can be detected from surprising distances. By moving gently, by drifting rather than swimming, these transparent creatures avoid announcing themselves. They become part of the background motion of the ocean itself, indistinguishable from the slow currents and settling particles around them. This strategy reveals something profound about the deep. In the absence of light, vision does not disappear. It changes. The deep ocean is not blind. It is hyper-aware of contrast, of motion, of any disruption in uniformity. To survive here is to minimize difference. The most successful animals are those that refuse to stand out. Their bodies tell a story of subtraction rather than addition. Evolution stripping away anything unnecessary until only function remains. Transparency is not weakness, it is refinement. But not all creatures choose to vanish. As effective as invisibility is, it has its limits. When food is scarce and encounters are rare, waiting unseen is not always enough. Some organisms have taken a very different path, one that seems at first to contradict everything about this dark world. Instead of avoiding light, they make it themselves, and in doing so, they turn the darkness into a tool rather than an obstacle. In a place where sunlight has never reached and never will, light itself becomes one of the rarest resources imaginable. That scarcity is exactly what gives it power. In the deep ocean, light is not decoration, not beauty, not something casually wasted. It is a tool sharpened by evolution, refined over millions of years into something precise and intentional. Where transparency allowed some creatures to vanish, others discovered that producing light could allow them to control the darkness instead. This is the realm of bioluminescence, and here it is not a gentle glow but a language, a lure, and sometimes a weapon. More than 90% of animals living in the deep ocean can produce light in some form. That alone should tell us how fundamental it is to survival. But the way they use it varies dramatically. Some produce brief flashes, sudden bursts meant to startle or confuse. Others glow steadily, faint and constant, marking their presence in a controlled way. And some wield light with unsettling sophistication, turning it into bait. The anglerfish is the most famous example, though fame hardly captures how strange it truly is. Drifting motionless in the dark, its body wide-mouthed and heavy, it expends almost no energy. Energy is precious here, and chasing prey would be wasteful. Instead, it waits. From its head extends a thin filament, like a fishing line, ending in a small fleshy bulb. Inside that bulb lives a colony of bioluminescent bacteria. The fish feeds them, shelters them, and in return they emit a soft, steady glow. To a smaller creature navigating the deep, this glow is irresistible. In a featureless blackness, any point of light becomes a focus of attention. It may resemble food, a smaller organism, or simply something worth investigating. As prey drifts closer, curiosity overcoming caution, the anglerfish remains perfectly still. Then, in a sudden movement, jaws snap shut, and the light vanishes along with the animal that followed it. The entire exchange costs the predator almost nothing. Light replaces motion. Patience replaces pursuit. Other hunters have taken this idea even further. Dragonfish, long and slender with bodies like living shadows, possess one of the most remarkable adaptations in the ocean. They are armed with enormous teeth that interlock like needles, but their true advantage lies beneath their eyes. There, hidden from casual view, are organs that emit a deep red light. This may not sound extraordinary until you consider the physics of the deep ocean. Almost all bioluminescence is blue or green because these wavelengths travel farthest through water. Over time, most deep-sea animals have evolved eyes sensitive only to those colours. Red light, which is quickly absorbed by seawater, is effectively invisible at depth. The dragonfish exploits this blind spot. It can see red light, its prey cannot. When it activates its red bioluminescent organs, it is effectively shining a private spotlight across the water. The world ahead of it becomes visible in sharp contrast, while everything it illuminates remains unaware that it is being seen at all. To the prey, the darkness remains complete. To the predator, it is suddenly structured and clear. This is not just camouflage or deception. It is a sensory monopoly, a way of owning information that no one else has access to. In the deep ocean, information is survival. Light is also used defensively. Some creatures release clouds of glowing particles when threatened, creating a luminous distraction that draws a predator's attention away from the fleeing animal. Others flash suddenly, overwhelming a predator's vision for just long enough to escape. There are species that use bioluminescence to communicate, signaling to mates with species-specific patterns of light that reduce the risk of being noticed by the wrong audience. In every case, the glow is controlled, intentional, and efficient. There is no wasted brightness here. Even beauty, when it exists, is incidental. What we find mesmerizing is for them purely functional. This reframes how we think about the deep. Darkness is not emptiness. It is a canvas on which light becomes meaningful. Every flash, every glow, every faint shimmer carries intent. It says, "Come closer," or "Stay away," or "I am here," or "You cannot see me seeing you." The deep ocean is not silent visually. It is whispering constantly in a language made of photons instead of sound. Yet even these hunters, these masters of deception and light, are only part of the story. Predators do not define an ecosystem on their own. For every hunter, there must be something to hunt, and beneath both lies a foundation that supports them all. In the deepest parts of the trench, far below where even these glowing hunters roam, life becomes slower, simpler, and stranger still. Down there, on the quiet seafloor, the story shifts away from pursuit and toward endurance. As the glowing hunters fade upward into the black water, the seafloor of the trench reveals itself as a different kind of world entirely. One defined not by pursuit or deception, but by patience and quiet persistence. This is the slow kingdom of mud, a vast plain of fine, pale sediment that stretches across the bottom of the Mariana Trench like an endless desert, interrupted only by subtle ripples and shallow depressions shaped by currents too weak to be felt above. At first glance, it appears almost lifeless, a still and featureless expanse where nothing moves and nothing happens. But this impression is deceptive. Life here does not announce itself. It works slowly, methodically, often on timescales that feel closer to geology than biology. The dominant residents of this realm are scavengers and processors, creatures whose entire existence revolves around extracting the last remaining traces of energy from whatever settles here. Sea cucumbers inch across the mud, their soft bodies pressing gently into the sediment as they ingest mouthfuls of silt, digesting the organic material within and leaving behind processed trails that subtly reshape the landscape. Their movement is so slow it is almost imperceptible, Yet over months and years they continuously turn the seabed, aerating it, redistributing nutrients, quietly maintaining the ecosystem. Nearby, brittle stars extend delicate arms from beneath the surface, sensing vibrations and chemical cues, withdrawing instantly if disturbed. Amphipods, some of them enormous by surface standards, roam the bottom in bursts of activity when food appears, then vanish again into the mud, conserving energy during long stretches of scarcity. But perhaps the most astonishing inhabitants of this slow kingdom are not animals in the way we usually imagine them at all. Scattered across the seafloor are structures that resemble sponges, flowers, or tangled root systems, rising gently from the sediment. Some look like pale lumps, others like intricate branching fans. They appear complex, architectural, almost designed, yet each of these structures is a single cell. Xenophyophores are among the largest single-celled organisms on Earth, some growing as wide as a dinner plate. They have no organs, no tissues, no nervous system. They are essentially enormous amoebas that have chosen one of the most extreme environments on the planet as their home. Their size is not a sign of complexity but of strategy. In a place where nutrients are scarce, surface area matters. Xenophyophores extend themselves across the mud, maximizing contact with the sediment and the water just above it, absorbing whatever organic particles they can find. To protect their fragile cellular bodies, they construct external shells called tests, but they do not grow these shells from within. Instead, they collect materials from their surroundings, carefully selecting grains of sand, fragments of shells, mineral particles, even microscopic debris, and cementing them together with secreted organic compounds. The result is a lattice-like structure that is strong yet porous, allowing water to flow through while shielding the cell inside. Each Xenophyophore is both builder and building, a living construction assembled from the remains of its environment. These structures provide more than protection. They create microhabitats, small pockets of complexity in an otherwise flat world. Tiny worms, crustaceans, and bacteria find refuge among the branches and cavities, turning each giant cell into a miniature ecosystem. In this way, the simplest life forms become architects of the deep, shaping the environment for others without intention or awareness. Movement in this kingdom is minimal because speed offers no advantage. Food does not flee here. It arrives slowly from above, settles, and waits to be processed. Energy conservation is the guiding principle. Metabolisms are slow, growth is gradual, and reproduction may take years or decades. Some organisms likely live far longer than their surface relatives, their lives stretched out by cold temperatures and limited resources. The trench floor is not a place of dramatic events, but of accumulation. Tiny changes add up over immense spans of time. Trails left by scavengers overlap and fade. Sediment shifts grain by grain. Life continues not by thriving exuberantly but by enduring. And all of this activity, from the largest single-celled builders to the smallest bacteria, depends on one quiet, almost invisible process that links the trench to the world above. A steady, delicate rain that never stops, even when the surface is calm, even when storms rage thousands of meters overhead. Everything here waits for it, lives on it, and is shaped by it. Beneath the slow kingdom of mud, below even the reach of the largest single-celled builders and the patient scavengers, there exists another world entirely, one that does not depend on falling food or drifting particles at all. It is a world hidden not just by depth, but by layers of sediment and rock, a biosphere sealed away from the surface ocean, operating in near silence and near stillness. For a long time, scientists believed life could not exist here. The assumption was reasonable. Without sunlight, without fresh organic material, without circulation, what energy could possibly sustain living systems? And yet, when researchers began drilling into the seafloor beneath trenches, pulling up cores of mud and fractured rock from meters below the ocean bottom, they found life. Not abundant, not fast, not familiar, but unmistakably alive. Tiny microbial cells appeared in places where nothing should have been able to grow. These organisms were not waiting at the surface of the sediment for marine snow to arrive. They were embedded deep within it, sometimes meters down, sometimes within microscopic cracks in solid rock. They were not connected to the surface food web at all. Instead, they seemed to be living on chemistry itself. Some of these microbes derive energy by stripping electrons from minerals, slowly altering the rock around them molecule by molecule. Others appear to use hydrogen produced by the interaction of water with certain types of rock, a reaction that releases small amounts of energy steadily over immense spans of time. There are even microbes that may survive on radiation, using the faint energy released by the natural radioactive decay of elements within the Earth's crust. This energy is incredibly weak, barely detectable by our instruments, but it is constant. For an organism whose metabolism has slowed to an almost unimaginable degree, it may be enough. These microbes do not live on human timescales. Some may divide once every 100 years, or once every 1,000. Their lives unfold so slowly that the distinction between biological and geological time begins to blur. To us, they appear almost dormant, but they are active in their own way, repairing damage, maintaining internal balance, persisting. They form what scientists sometimes call a shadow biosphere, not because it is sinister, but because it exists alongside the more familiar ecosystem without interacting with it. The creatures of the mud live on leftovers from above. These microbes live on the planet itself. Their isolation raises profound questions about the nature of life. If organisms can survive here, sealed away from sunlight and surface chemistry, then life may not require the conditions we once thought essential. It may be enough to have energy, however faint, and time, however vast. This idea reshapes how we think not only about Earth, but about other worlds. Beneath the icy shells of distant moons, similar slow ecosystems could exist, hidden in rock and darkness, living quietly for billions of years. The trench thus becomes more than an extreme environment. It becomes a window into alternative ways of being alive. But even in this world of scarcity and patience, the rules are occasionally broken. The deep is not always defined by slow accumulation and quiet endurance. From time to time, something extraordinary happens. A sudden, massive delivery of energy arrives from above, overwhelming the careful balance of starvation that defines life here. It is rare, unpredictable, and transformative. When it happens, the trench responds not with subtlety, but with urgency, as if an entire ecosystem wakes at once. What follows is one of the most dramatic events in the deep ocean, a moment when abundance floods a world built on waiting and everything changes. In a world defined by waiting, there are moments when patience is suddenly rewarded beyond anything the ecosystem is built to handle. Far above the trench, in the sunlit surface waters, a whale dies. It may be old, sick, injured, or simply at the end of a long life. When it does, gravity takes over. The massive body, sometimes weighing more than 70 tons, begins a slow descent through the water column. At first it sinks gently, passing through the bright zone where fish still scatter and light still filters down. Over hours and then days it drifts lower, through the twilight zone where the last hints of blue fade away, and into the blackness where nothing living sees it coming. The descent can take days. As it falls, pieces may be stripped away by scavengers, but much of the body remains intact, a vast reservoir of energy moving steadily toward the seafloor. When it finally reaches the bottom of the trench, the impact is not violent in the way a crash on land would be. The water cushions it, the mud receives it. But ecologically it is an earthquake. In a single moment, a barren stretch of sediment is transformed into the richest location for hundreds of meters around. More organic material has arrived than would normally fall on that spot in centuries. The scent spreads quickly, carried by faint currents, chemical signals moving outward through the darkness. Scavengers are the first to respond. Giant amphipods arrive in swarms, pale and armoured, tearing into the soft tissue. Snailfish appear, as do deep-sea sharks if the depth allows, all converging on this sudden feast. For months, sometimes more than a year, the carcass is stripped of flesh. The activity is intense by deep-sea standards, a rare frenzy in a world that usually moves at a crawl. Once the soft tissue is gone, the ecosystem does not collapse. It changes. The second stage begins as smaller organisms move in, feeding not on the whale itself but on the enriched sediment around it. The decay has infused the surrounding mud with nutrients, fueling blooms of bacteria and attracting worms, crustaceans and other invertebrates that thrive in this temporary abundance. This stage can last years. Then, when even that energy begins to fade, the most remarkable transformation occurs. What remains is the skeleton, massive bones packed with fats and oils locked inside. These lipids leak slowly into the surrounding sediment, creating conditions similar to those found at hydrothermal vents. Chemosynthetic bacteria colonize the bones, feeding on the released chemicals. In turn, they support specialized organisms found almost nowhere else. Osedax worms, often called zombie worms, settle on the bones and bore into them, lacking mouths or digestive systems of their own, relying entirely on symbiotic bacteria to process the nutrients. Clams and mussels appear, anchoring themselves to the skeleton. The whale's remains become a reef, a city of life sustained not by sunlight or falling snow, but by death itself. This final stage can persist for decades, sometimes up to a century. Long after the event that created it has been forgotten by the surface world, the whale fall continues to shape life in the deep. For creatures adapted to starvation, it is a miracle. But miracles like this are rare, unpredictable and temporary. The trench has evolved around scarcity, not abundance. And now, into this carefully balanced system, humans have introduced their own versions of falling mountains. Not gifts, but remnants. Objects that descend not once, but endlessly. Materials that do not decay, do not nourish, do not vanish. They sink quietly, just as the whale did. But instead of becoming cities of life, they become something else entirely. The trench accepts them all the same. Once something enters the trench, it almost never leaves. This is not because the water is still or the currents are weak, but because of the trench's shape and gravity's quiet persistence. The Mariana Trench is not a flat basin where material can drift in and out. It is a vast, sloping funnel carved into the Earth's crust, a V-shaped wound that guides everything downward. Particles falling from above do not scatter evenly across the ocean floor. They slide, roll, and settle deeper, pulled by gravity along subtle gradients that eventually lead to the lowest point. Over time, this makes the trench a natural collector, a place where material accumulates simply because there is nowhere further to go. Fine sediments drift down and slide into its depths. Organic matter settles and concentrates, and so do the things we never intended to send there. Pollutants released at the surface do not vanish when they sink. Many bind easily to particles of organic matter or sediment. Heavy metals, like mercury and lead, cling to microscopic debris. Persistent organic pollutants attach to marine snow. Plastic fragments, broken down into ever smaller pieces, drift downward for months or years until they finally reach the bottom. The trench gathers all of it. Once there, the cold temperatures and low oxygen slow chemical reactions and biological breakdown. Things decay slowly. Plastics remain intact far longer than they would in shallow water. Metals corrode, but the process is measured in decades, not months. The trench becomes not just a sink, but a long-term archive of everything that falls into it. This would matter less if the trench were lifeless, but as we've seen, it is not. Its food web is slow, sparse, and patient, built around scarcity and recycling. When pollutants arrive, they enter that same system. Heavy metals absorbed by sediment are taken up by bacteria and single-celled organisms. Those are eaten by small invertebrates. Those are consumed by larger scavengers. With each step, the concentration increases. This process, known as bioaccumulation, is especially pronounced in the deep because organisms live longer and metabolize more slowly. Toxins remain in their bodies for years. There is little opportunity to dilute or flush them away. Studies have found elevated levels of persistent pollutants in amphipods, collected from the deepest trenches, sometimes higher than those measured in coastal environments, thousands of kilometers from any source of contamination. These creatures are not exposed to pollution because they live near humans. They are exposed because gravity delivers our waste to them eventually, no matter how far away they are. The trench does not discriminate between natural and artificial falls. It accepts everything equally. This changes how we must think about remoteness. Distance does not protect the deep. Isolation does not equal immunity. The same processes that deliver whale falls and marine snow also deliver microplastics and industrial chemicals. The difference is that one nourishes life and eventually disappears, while the other lingers and alters the system in ways we are only beginning to understand. And yet, even as we recognize this accumulation, another shift is taking place. The trench is no longer viewed only as a place that receives what we discard. Increasingly, it is seen as a place that holds resources we want. The same geological processes that create hydrothermal vents and unique ecosystems also concentrate valuable minerals. The very features that made the trench inaccessible now make it attractive. As technology advances, the question is no longer whether we can reach these depths, but whether we should disturb them. The trench has always been a collector. Now it risks becoming a target. For most of modern history, the deep ocean was treated as a place to forget things, a convenient nowhere that could absorb whatever the surface world no longer wanted to see. Broken ships, unwanted chemicals, even radioactive waste were sent down with the quiet confidence that distance and pressure would make them vanish from relevance. But perspective has a way of changing when technology advances. As our ability to reach the deep improves, the trench is no longer viewed only as an endpoint. It is being reimagined as a storehouse, a vault filled with materials formed under conditions that do not exist anywhere else on Earth. The same hydrothermal systems that create oases of life also concentrate minerals with remarkable efficiency. When superheated water circulates through the crust, it dissolves metals from the surrounding rock. As that fluid erupts back into near-freezing seawater, Those dissolved elements precipitate out, settling around the vent structures and slowly building dense mineral deposits. Over thousands and millions of years, this process creates towering chimneys and massive mounds rich in copper, zinc, iron, silver, and gold. More importantly for the modern world, they contain rare earth elements and cobalt, materials essential for batteries, electronics, renewable energy systems, and advanced manufacturing. On land, these resources are increasingly difficult to access without enormous environmental and social costs. Mines scar landscapes, pollute waterways, and disrupt communities. In contrast, the deep ocean appears, at least on paper, empty and remote. The idea of harvesting minerals from a place few people will ever see has an unsettling appeal. It promises abundance without obvious sacrifice. Companies and governments have taken notice. Exploration licenses have been issued. Prototype machines have been tested. Plans have been drawn for enormous robotic vehicles capable of descending thousands of meters, grinding vent structures into slurry, and pumping the material back to the surface through long hoses. The language used to describe this effort is often careful and technical. It speaks of efficiency, minimal impact, and progress. But beneath that language lies a reality that is harder to soften. Hydrothermal vents are not inert rock formations waiting to be collected. They are living systems. The organisms that inhabit them are uniquely adapted to their chemistry, many found nowhere else on Earth. Tube worms, blind crabs, specialized clams, and entire microbial communities depend on the steady flow of chemical energy these vents provide. To remove the vent is to remove the ecosystem. Unlike forests or reefs in shallow water, these systems do not recover quickly. Vents form slowly. Their communities assemble over long periods. Destroying one is not a temporary disturbance. It is closer to erasing a library of biological solutions written over millions of years. The physical act of mining would also send plumes of sediment into the surrounding water. Fine particles stirred up by grinding and excavation do not settle immediately. They can drift for kilometers, smothering nearby habitats, clogging the feeding structures of filter feeders, and altering chemical balances in ways that ripple outward. In the deep ocean, where currents are slow and life is adapted to stability, such disturbances linger. Recovery, if it happens at all, may take centuries. There is also the question of knowledge. We're only beginning to understand how these ecosystems function. Many species have been observed only a handful of times. Some are known from a single sample or image. To mine before understanding is to accept loss without knowing what is being lost. The irony is difficult to ignore. The trench became a dumping ground because it was seen as empty and resilient. Now it is seen as valuable for the same reason. Both views underestimate the complexity of what exists there. Both assume that depth equals disposability. The difference now is scale. Extraction would not be accidental or passive. It would be deliberate, systematic, and industrial. The trench has absorbed our waste quietly. It will not resist our machines, but silence should not be mistaken for consent. Every action in this environment echoes longer and farther than it would at the surface. And as plans for extraction advance, questions of protection, responsibility and restraint become impossible to avoid. The trench has already been shaped by human presence in ways we did not intend. What happens when we begin shaping it on purpose remains an open and deeply consequential question. The idea of protection feels solid when it exists on paper. Lines drawn on maps give the impression of control, of intention made real through borders and designations. On land, a protected area can be fenced, patrolled, marked with signs. Its edges are visible, its violations can be seen and measured. In the deep ocean, and especially around the Mariana Trench, protection exists in a far stranger form. There are no fences at 7 miles down, no gates, no visible boundaries separating what is preserved from what is permitted. The trench lies partly within national jurisdictions and partly beyond them, crossing into international waters where responsibility is shared, diffused, and often delayed. Marine protected areas may cover sections of the trench, declared sanctuaries meant to safeguard ecosystems from fishing, mining, or other exploitation. But these protections assume a kind of stability that the ocean does not respect. Water moves, sediment drifts, chemistry spreads. When disturbance occurs near a boundary, its effects do not stop at an invisible line. A plume of sediment stirred up by mining or drilling does not check a map before dispersing. It flows with currents, settling wherever gravity and turbulence carry it. In the trench, where the seafloor slopes inward, these plumes are naturally funneled downward toward the deepest point, regardless of where they originate. This means activity outside a protected area can easily impact what lies within it. The physics of the environment overwhelms the logic of policy. Enforcement presents another challenge. Monitoring activity at extreme depths requires specialized ships, equipment, and constant attention. Even with satellites tracking surface vessels, what happens kilometers below remains difficult to verify in real time. Autonomous machines can operate beyond human observation. Data can be delayed, incomplete, or classified. In international waters, authority is fragmented among nations and organizations, each with different priorities and incentives. The result is a gap between intention and outcome, where protections exist largely as agreements rather than guarantees. This gap grows wider as industrial interest accelerates. The trench is no longer simply remote, it is strategically valuable. That value complicates restraint. When resources are scarce elsewhere, pressure builds to access what lies beyond easy reach. Rules written for a slower era struggle to adapt to rapidly advancing technology. Even well-meaning protections can lag behind reality, responding after damage has already occurred. And yet, the trench resists simplification. It is not just a resource, not just a dumping ground, not just a scientific curiosity. It has become something symbolic, a place where the limits of our control are exposed. The difficulty of protecting it forces a confrontation with uncomfortable truths, that we can reach places we cannot effectively govern, that our influence extends farther than our understanding, that some environments operate on scales of time and sensitivity that do not align with human decision-making. The trench reveals the mismatch between our systems and the planet's processes. It shows how lines drawn by humans dissolve under pressure, motion, and depth. In this sense, the trench becomes more than a physical location. It becomes a mirror. It reflects how we think about responsibility in spaces that do not belong to any one nation, and how we act when consequences are distant, delayed, and unseen. The failure of protection lines is not just a technical problem. It is a philosophical one. It asks whether preservation can exist without visibility, whether stewardship is possible without presence, whether restraint can hold when opportunity appears boundless. As the trench absorbs everything that reaches it, from drifting particles to ambitious plans, it quietly challenges the idea that we can divide the world cleanly into zones of use and zones of care. Down there, the distinction blurs. Everything connects, everything settles, and what we choose to do above eventually arrives below, indifferent to our categories. The Mariana Trench did not become symbolic because of a single discovery or a single story. but because it embodies something older and more difficult to name. Long before we had submersibles or sonar or maps detailed enough to show its outline, humans sensed that there were places on Earth that did not acknowledge us. Places that existed entirely on their own terms, untouched by intention or meaning. The trench represents that idea in its purest form. It is vast without being dramatic, powerful without being aggressive, ancient without offering wisdom. It does not threaten. It does not invite. It simply exists. And that quiet indifference has always unsettled us more than any monster ever could. We are a species that looks for response. We expect the world to react to us, to reward effort, to punish mistakes in ways we can understand. Mountains can be climbed, storms can be waited out. Even space, as empty and hostile as it is, offers a kind of dialogue. We send machines, we receive data. There is feedback. The trench offers almost none. It absorbs sound, light, debris, ambition, and leaves no obvious trace of acknowledgement. When humans first imagined the abyss, they filled it with monsters, not because the deep suggested danger, but because danger felt easier to process than silence. A creature can be fought, feared, or defeated. Indifference cannot. The idea that something exists so close to us, on our own planet, yet remains fundamentally unconcerned with our presence, challenges a deep assumption we carry without realizing it, that we matter everywhere. The trench quietly contradicts that assumption. It reminds us that the Earth was not made for us, and that most of it functions perfectly well without ever noticing we are here. This is not a malicious truth. The trench is not hostile in the way fiction often portrays the unknown. There is no intent behind the pressure, no cruelty in the darkness. The forces at work there are simply physics and time operating steadily, impartially. That is what makes the place powerful as a symbol. It strips away narrative. It refuses to cast us as protagonists. In the trench, we are visitors at best, anomalies passing briefly through an environment that has existed for tens of millions of years and will continue long after we are gone. This realization produces fear in some and fascination in others. For many, it is both at once. Writers like H.P. Lovecraft understood this intuitively. When he searched for a setting that could hold something truly alien, something that was not evil but utterly unconcerned with humanity, he chose the deep ocean. Not because it was violent, but because it was indifferent. His fictional abyss resonated because it echoed a real one. The fear was never about what might be waiting there. It was about the possibility that nothing was waiting at all, that there is no audience, no meaning imposed from outside, no response to our curiosity except silence, and yet that same silence has guided discovery. The trench has drawn explorers not in spite of its indifference, but because of it. Scientists are compelled by places where assumptions fail, where life survives without sunlight, where chemistry behaves differently, where ecosystems function on patience rather than abundance. The trench forces us to confront how little we know, and in doing so it expands the boundaries of knowledge. It teaches us that mystery does not require threat to be profound, that not knowing is not a weakness, but a starting point. In recent years, this perspective has shifted how we approach exploration beyond Earth. When we look at icy moons like Europa or Enceladus, with their hidden oceans and crushing pressures, we no longer dismiss them as too extreme. We recognize the pattern. We've already seen life adapt to darkness, pressure, and chemical energy. The trench has prepared us to imagine life where imagination once failed. In this way, fear becomes a guide rather than an obstacle. The unease we feel toward the abyss sharpens our questions. It reminds us to proceed carefully, to observe before acting, to listen before extracting. The trench's symbolism is not just about insignificance, it is about humility. It suggests that there are places where understanding must come before use, where restraint is not weakness but respect. As we continue to explore, both on our planet and beyond it, the trench stands as a reminder that the unknown does not exist to be conquered. Sometimes it exists simply to be acknowledged, to sit with the discomfort of not being central, to learn that mystery without malice can still be meaningful, and that in the quiet presence of something vastly larger than ourselves, we may discover a clearer sense of where we truly stand. As our understanding of the Mariana Trench deepens, it begins to serve a purpose that extends far beyond Earth itself. What we have learned in this dark, pressurized abyss has quietly reshaped the way scientists think about life elsewhere in the universe. For much of human history, the search for extraterrestrial life focused almost entirely on planets that resembled our own, worlds bathed in sunlight, with breathable atmospheres and surface oceans. Darkness was treated as a barrier, pressure as a limit, cold as a dead end. The trench has dismantled those assumptions piece by piece. Here, on our own planet, life thrives without sunlight, without warmth, without the conditions we once believed were essential. It survives on chemistry, on heat leaking from rock, on patience measured in centuries, and in doing so, it has provided a living blueprint for what alien oceans might contain. When scientists talk about Jupiter's moon Europa or Saturn's moon Enceladus, they no longer speak in purely speculative terms. These are no longer abstract ideas or distant points of light. Both moons are now known to harbour vast oceans of liquid water beneath thick shells of ice. Europa's ocean may be deeper than all of Earth's oceans combined, kept liquid by tidal heating as Jupiter's immense gravity flexes its interior. Enceladus actively vents plumes of water vapour, ice particles, and organic molecules into space, evidence of hydrothermal activity on its ocean floor. In other words, they possess the same fundamental ingredients that sustain life in the Mariana Trench: liquid water, chemical energy, and long-term stability. There is no sunlight beneath Europa's ice. There is no photosynthesis. If life exists there, it must resemble the life we find at Earth's greatest depths, rather than anything that swims near the surface. It would be microbial, perhaps gelatinous, adapted to pressure, reliant on chemistry rather than light. The trench has already shown us that such life is not only possible but resilient. Chemosynthetic bacteria at hydrothermal vents form the base of entire ecosystems. Animals that depend on them do not merely survive, they diversify, specialize, and persist. This realization has transformed the Mariana Trench into a proving ground for astrobiology. Instruments designed to search for life on distant moons are first tested here. Sampling techniques, autonomous navigation systems, pressure-resistant materials, and biochemical detection methods are refined in the trench before they're ever launched into space. It is the closest analogue we have to an alien ocean, accessible enough to study, yet extreme enough to challenge every assumption we bring with us. Even the way we interpret signals has been shaped by trench research. On Europa or Enceladus, a sign of life is unlikely to be a fish or a plant. It will be chemical imbalances, unexpected heat signatures, or microbial communities clustered around vents. These are exactly the kinds of clues scientists have learned to recognize by studying Earth's deepest environments. The trench has taught us that life does not announce itself loudly. It leaves subtle fingerprints, patterns that only make sense once you understand the environment that produced them. There is also a philosophical shift that comes with this comparison. Exploring the trench has shown us the limits of direct human presence. We cannot swim there, we cannot build cities there, we can barely visit. Instead, we rely on machines, on patience, on careful observation. This mirrors how exploration of alien oceans will unfold. There will be no heroic descents by astronauts into Europa's sea. There will be probes, robots, swarms of autonomous explorers making decisions far from Earth. The trench has forced us to accept this model, to let go of the idea that discovery requires physical conquest. It has taught us to design exploration around respect for an environment's constraints rather than attempts to overpower them. In this way, the Mariana Trench is not just a subject of study, it is training. It prepares us technologically and mentally for encounters with worlds that do not revolve around us. It reminds us that life can be quiet, slow, and deeply strange, and still be life. As we look outward, the lessons of the trench suggest that the universe may be more alive than it appears, but only if we learn how to look properly. And to do that, our approach to exploration itself must evolve. We cannot rely on brute force or constant presence. We must become observers rather than occupiers, listeners rather than extractors. The trench has already shown us what happens when we underestimate a silent world. If we are to explore others, we will need to change how we go down, how we look, and how we leave. The future of exploration is becoming quieter, less theatrical, and far more patient, shaped not by the image of a lone human descending heroically into darkness, but by fleets of machines moving carefully, almost humbly, through environments that do not belong to us. The Mariana Trench has played a central role in this shift because it has made clear the limits of human presence. We're not built for sustained existence under crushing pressure, nor are we efficient observers in places where every second of survival requires enormous engineering. The great manned descents captured imagination, but they were rare, expensive, and fragile moments. The trench itself has taught us that understanding does not require dominance, and that the most effective way to learn is often to let go of the need to be there ourselves. Autonomous probes are now the primary explorers of the deep, machines capable of descending without tethers, making decisions without constant human input, and operating for weeks or months at a time. Unlike earlier remotely operated vehicles which were constrained by cables and surface commands, these probes are designed to think locally. They adjust buoyancy, alter course, and prioritize observations based on what they encounter. In the trench, where radio communication is impossible, and even sound travels unpredictably, this autonomy is not a luxury, but a necessity. The machines must be able to respond to the environment as it is, not as we imagine it from above. Increasingly, exploration is moving away from the idea of a single expensive vehicle and towards swarms of smaller ones. Instead of one spotlight scanning a vast darkness, dozens or hundreds of small points of light move together, sharing information, mapping terrain collaboratively, and adapting as a group. If one is lost, the mission continues. If one finds something unusual, others converge. This distributed approach mirrors the deep itself, where no single organism dominates and survival depends on networks rather than individuals. It is also how future missions to alien oceans are likely to unfold, with swarms released beneath ice shells spreading out to search for vents, chemical gradients, or signs of life. The design of these machines has begun to change as well, influenced directly by the biology of the trench. Engineers are moving away from rigid armoured forms towards soft robotics, machines made of flexible materials that compress rather than resist, bend rather than break. Inspired by squid, octopus and gelatinous fish, these robots can withstand pressure by yielding to it. Their movements are slow and efficient, conserving energy, minimizing disturbance, and allowing them to slip through narrow spaces without damaging fragile surroundings. In many ways, they're becoming less like tools and more like temporary residents, shaped to coexist with the environment rather than impose themselves on it. Sensors too are becoming more subtle. Instead of blasting the darkness with powerful lights and sonar, newer systems listen passively, sampling water chemistry, detecting faint thermal differences, and observing bioluminescent signals without overwhelming them. The trench has shown us that observation itself can be disruptive, that even light is an intrusion in a world that evolved without it. Learning from the abyss means learning restraint. It means accepting that some data will be incomplete, some mysteries unresolved, and some systems better left undisturbed. This philosophy marks a profound change in how exploration is framed. The goal is no longer to conquer or to extract, but to understand without erasing. The quiet future of exploration is not driven by spectacle, but by continuity. Machines return again and again to the same places, building long-term records of change, watching slow processes unfold over years instead of minutes. This patience aligns more closely with the trench itself, where nothing happens quickly and everything matters over time. As this approach takes hold, the Mariana Trench becomes less of a frontier and more of a teacher. It has forced us to confront the inadequacy of loud, forceful methods in subtle environments. It has shown us that the deepest insights often come from listening rather than acting. And as we carry these lessons forward into deeper oceans and distant worlds, the trench remains quietly present in the background, reminding us that progress does not always mean moving faster or going farther, but sometimes learning how to move more gently through places that will outlast us. What the Mariana Trench ultimately teaches us does not arrive as a revelation or a solved equation, but as a slow accumulation of understanding that settles gently, the way sediment settles on the trench floor itself. Over time, as we've descended layer by layer, the picture that emerges is not one of conquest or completion, but of humility. We thought the deepest place on Earth would be empty, silent, hostile, perhaps even monstrous, and instead we found it full, active, and quietly complex. We discovered life where life should not work, chemistry where sunlight never reaches, ecosystems powered by patience rather than abundance. We learned that maps can lie, that vast portions of our own planet remain interpreted rather than truly seen, and that pressure, not distance, is often the greatest barrier to understanding. We learned that sound travels farther in the deep than light ever could, that the ocean listens to itself constantly, and that not every noise has a name or an explanation. We learned that the myths of giant predators tell us more about our imagination than about reality, while the real giants move slowly, softly, and without drama. We followed the first humans who dared to go down, trusting engineering more than instinct, descending into darkness so complete it erased any sense of up or down, and we shared the unease of that unexpected crack, that moment of doubt that reminded us how thin the boundary is between presence and absence. We carried that unease forward into modern descents, into solitary capsules where isolation becomes physical, where the environment offers no acknowledgement at all. and where indifference itself becomes the dominant sensation. We looked at the most disturbing discoveries not because they were alien, but because they were familiar, human debris resting quietly at the bottom, arriving before we ever did, reminding us that our influence moves faster and farther than our intentions. We watched the planet recycle itself through subduction, felt earthquakes that should not exist, saw heat leak from the Earth's interior through chimneys that should not support life, and learned that physics bends in ways that feel almost wrong when pressure rewrites the rules. We entered the Hadal zone and saw why surface life fails there, then stayed long enough to understand how other life thrives by rewriting itself at the molecular level. We met predators so soft they would collapse at the surface, creatures that erased themselves through transparency, others that spoke in light instead of sound, turning darkness into a tool rather than a limitation. We slowed down on the seafloor, watching mud become a kingdom, single cells become architects, and death become a city when a whale fell from the sky and nourished life for decades. We looked beneath even that, into rock and sediment where microbes live on geological time, dividing once in centuries, reminding us that life does not have to hurry to persist. Saw how the trench never lets go, how it gathers everything, good and bad, how pollution and heavy metals settle into the same slow food web that sustains life, how distance does not equal protection. We followed the shift from dumping ground to treasure chest, watched interest turn toward extraction, and understood how easily curiosity becomes appetite. We traced the failure of protection lines, saw how physics ignores policy, how sediment plumes drift across invisible borders, and how responsibility becomes diffuse where ownership disappears. Somewhere along the way, the trench stopped being just a place and became a symbol, a mirror reflecting our discomfort with vastness that does not care about us, with mystery that offers no threat yet no reassurance. We saw how that discomfort does not have to paralyze us, but can guide us, shaping how we explore alien oceans, how we design machines that yield instead of resist, how we replace heroes with swarms, force with listening, presence, with patience. And through all of this, one lesson repeats itself quietly without insisting on being learned. We have not solved the planet. The Earth is not finished, not fully known, not wrapped up in satellite images and neat diagrams. Mystery is not a failure of science, but one of its most valuable products. The trench reminds us that not knowing everything keeps curiosity alive, keeps restraint relevant, keeps wonder intact. It suggests that there is value in leaving some questions open, some places unexploited, some silences unbroken. As this journey slows, as attention drifts back upward through layers of water and thought, what remains is not fear, not triumph, but a steady calm. The knowledge that beneath the noise of the surface world, beneath urgency and explanation, there is a deeper rhythm playing out on its own terms, ancient, patient, and unconcerned. The Mariana Trench will continue whether we watch it or not, listening to the planet, recycling its crust, hosting life that moves too slowly for us to notice unless we choose to slow down too. And perhaps that is its final lesson, offered without demand, that understanding does not always require answers, and rest does not always require closure. Sometimes it is enough to know that something vast exists below us, quietly reminding us that the world is larger, deeper, and more mysterious than we will ever fully grasp. There is a quiet comfort in knowing that there will always be something deeper, something beyond the edge of what we can fully understand. As this long descent begins to slow, As attention drifts upward again through miles of dark water and accumulated thought, the Mariana Trench remains below, unchanged by our curiosity, unmoved by our conclusions. It does not need us to finish the story. It is content to continue without resolution. And in that, there is a strange kind of reassurance. We live in a world that constantly pushes toward answers, toward clarity, toward closure. We are taught to solve, to define, to complete. But the trench offers a different rhythm. It shows us that some things are not meant to be exhausted by explanation, that mystery is not a gap to be filled, but a space to rest in. Down there, darkness is not an absence. It is a condition, as necessary as light is at the surface. Without darkness, there would be no deep currents of sound, no bioluminescent language, no soft-bodied life yielding perfectly to pressure, no slow kingdoms of mud quietly recycling the planet one grain at a time. Without darkness, there would be no place for patience to matter. The trench reminds us that not everything needs to be illuminated to be real. That unseen processes are often the ones holding everything else together. It is easy to forget this in a world that never truly sleeps, where artificial light erases night and constant information erases silence. But far below, the earth continues its older patterns, indifferent to urgency, steady in its motion. Plates slide at the speed of growing fingernails. Heat leaks slowly from the planet's interior. Life divides on timescales that make human lifespans feel brief and loud. Nothing is rushed. Nothing is wasted. Even endings become beginnings, as whale falls turn death into decades of nourishment, as discarded material becomes sediment, as sediment becomes rock, as rock is eventually drawn back into the mantle. In this vast cycle, our presence is fleeting, but not meaningless. The trench does not judge what we send down, but it does record it. It holds our curiosity alongside our carelessness, our instruments alongside our debris, our questions alongside our answers. And perhaps that is why it lingers in the mind long after the facts fade. It is not frightening because it is dangerous. It is unsettling because it does not respond. It does not reflect our importance back to us. It simply continues. Yet that very indifference can be grounding. In a world that often feels overwhelmed by human concerns, by noise, speed, and expectation, the existence of the place so vast and so unconcerned offers relief. It reminds us that the planet is larger than our worries, deeper than our fears, and more resilient than our mistakes, even as it quietly absorbs them. The idea that there is always something deeper does not diminish what we know. It gives it context. Knowledge becomes less about ownership and more about relationship. Understanding becomes something we approach gently, knowing it will always be partial, always evolving. As this journey settles, as thoughts slow to match the pace of the deep, it is enough to carry one's simple awareness. Beneath the surface of everything familiar, there are layers we have not touched, rhythms we have not learned, and stories unfolding without an audience. The Mariana Trench is one of those stories. It does not ask to be finished. It does not demand attention. It waits quietly, patiently, reminding us that darkness is not something to fear, but something to respect, and that mystery, far from being a problem to solve, can be a place to rest.